here. Um, so last time I think um, I had troubles running the test cases because of Mac OS. So I'm on Windows right now. And what else? I'm gonna watch lecture 7, and then I'm gonna go back to the problem set. I fixed the test case is not running on Windows. Was pretty simple to fix. I just had to use an older Python version. That was about it basically. And then yeah, so I'll watch lecture 7, which is called confidence intervals, and then basically start solving PSET 3, right? So let's see if I do main display. Nope, display capture. Yep. Okay. So
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Hi, everybody. Welcome back to class. I have a lot to cover today, so I'm just going to get right to it. So you may remember at the end of last lecture, I talked about the empirical rule and said that there were a couple of assumptions underlying it, that one is that the mean estimation error is 0, and second, that the distribution of errors will be normally distributed. I didn't probably mention at the time, but we often call this distribution Gaussian, after the astronomer Carl Gauss. And it looks like that. Normal distributions are very easy to generate in Python. I have a little example here of generating not a real normal distribution, but a discrete approximation of one. And the thing to really notice about it here is this line, random.gauss. So that's a built-in function of the random library. The first argument is the mean, and the second argument is the standard deviation, or mu and sigma, as they're usually called. Every time I call that, I will get a different, or usually a different random value drawn from a Gaussian with a mean, in this case, of 0, and a standard deviation of 100. I'm then going to produce a plot of those so you can see what it looks like. And I'm going to do that using some things we haven't seen before. So first of all, we've seen histograms. So pylab.hist produces a histogram. Bins tells us how many bins we want in the histogram. I said we want 100. The default is 10. Dist is the values it will use for it. And then this is something we haven't seen before, weights. Weights is a keyword argument. So normally, when we produce a histogram, we take all of the values, the minimum to the maximum, and in this case, we would divide them into 100 bins, because I said bins equals 100. And then we would, so the first bin might be, well, let's say we only had values ranging from 0 to 100. The first bin would be all the zeros, all the ones, up to all the 99s. And it weights each value in the bin by 1. So if the bin had 10 values falling in it, the y-axis would be at 10. If the bin had 50 values falling in it, the y-axis would go up to 50. You can tell it how much you want to weight each bin, the elements in the bins, and say, no, I don't want them each to count as 1. I want them to count as a half or a quarter. And that will change the y-axis. So that's what I've done here. What I've said is I've created a list, and I want to say for each of the bins, in this case, I'm going to weight each of them the same way. The weight is going to be 1 over the number of samples. I'm multiplying it by the len of dist. That will be how many items I have, and that will tell me how much each one is being weighted. So for example, if I have, say, 1,000 items, I could give 1,000 values and say I want this item weighted by 1, and I want this item over here weighted by 12 or a half. We rarely do that. Usually what we want is to give each item the same weight. So why would I want it not to be weighted at just 1? Because I want my y-axis to be more easily interpreted as essentially giving me the fraction of the values that fell in that bin. And that's what I'm doing here. The other new thing I'm doing here is the plotting commands, including pylab.hist, many of them return values. Usually I just ignore that value and we just say pylab.plot or pylab.hist. Here I am taking the value. The value in this case for a histogram is a tuple of length 2. The first element is a list or an array giving me how many items are in each bin. And the second is the patches used to produce the beautiful pictures we're used to seeing. So here what I'm going to do is take this value so that I can do this at the end. Now, why would I want to look at the fraction within approximately 200 of the mean? What is that going to correspond to in this case? Well, if I divide 200 by 2, I get 100, which happens to be the standard deviation. So in this case, what I'm going to be looking at is what fraction of the values fall within 2 standard deviations of the mean. Kind of a check on the empirical rule, right? All right. When I run the code, I get this. So it is a discrete approximation to the probability density function. You'll notice, unlike the previous picture I showed you, which was nice and smooth, this is jaggedy. You would expect it to be. And again, you can see it's very nice that the peak is what we said the mean should be, 0, and then it falls off, and indeed, slightly more than 95% fall within 2 standard deviations of the mean. Not even surprised that it's a little bit more than 95% because, remember, the magic number is 1.96, not 2. But since this is only a finite sample, I only want it to be around 95. I'm not going to worry too much whether it's bigger or smaller. All right? So random.gauss does a nice job of giving us Gaussian values. We plotted them. And now you can see that I've got the relative frequency. That's why I see fractions on the y-axis rather than counts. And that was because of the way I used the weights command. All right, let's return to PDFs. So as we said last time, distributions can be defined by probability density functions. That gives us the probability of some random variable lying between 2 values. It defines a curve where the values in the x-axis lie between the minimum and maximum values of the variable. And it's the area under the curve, and we'll come back to this, between those 2 points that give us the probability of an example falling in that range. So now let's look at it for a normal distribution. You may recall from the last lecture this rather exotic-looking formula, which defines a PDF for a normal distribution. And here's some code that's as straightforward an implementation as one could imagine of this formula. Okay, so that now is a value that, given a mu and a sigma and an x, gives me the x associated with that mu and sigma. Okay? And you'll notice there's nothing random about this. All right, it is giving me the value. Now, let's go down here. And I'm going to, for a set of x's, get the set of y's corresponding to that, and then plot it. I'm going to set mu to 0 and sigma to 1, a so-called standard normal distribution. And I'm going to look at the distribution from -4 to 4. Nothing magic about that other than, as you'll see, it's kind of a place where it asymptotes near 0. So while x is less than 4, I'll get the x value. I'll get the y value corresponding to that x by calling Gaussian, increment x by 0.05, and do that until I'm done. And then simply I'll plot the x values against the y values and throw a title on it using pylab.title. All right, does code make sense? Well, this is where I got that beautiful picture we've looked at before. When I plot it here, it actually looks quite smooth. It's not. It's really connecting a bunch of tiny little lines, but I made the points close enough together that it looks, at least here, smooth at this resolution. So we know what the values are on the x-axis are. Those are the values I happen to want to look at from -4 to 4. What are the values on the y-axis? We kind of would like to interpret them as probabilities, right? But we could be pretty suspicious about that. And that if we take this one point that's up here, we say the probability of that single point is 0.4. Well, that doesn't make any sense. Because in fact, we know the probability of any particular point is 0 in some sense, right? So furthermore, if I chose a different value for sigma, I can actually get this to go bigger than 1 on the y-axis. So if you take sigma to be, say, 0.1, I think the y-axis goes up to something like 40. So we know we don't have probabilities in the range 40. So if these aren't probabilities, what are they? What are the y values? Well, not too surprising, since I claimed this was a probability density function. They're densities. Well, what's a density? If this makes sense, I'll say it, and then I'll try and explain it. It's a derivative of the cumulative distribution function. Now, why are we talking about derivatives in the first place? Well, remember what we're trying to say. If we want to say, ask what's the probability of a value falling between here and here, we claim that that was going to be the area under this curve, right? The integral. Well, as you know from 1801, there's a very clear relationship between derivatives and integrals. And so if we interpret each of these points as a derivative, in some sense the slope here, then we can look at this as the area just by integrating under there. So to interpret a PDF, we always do it mathematically. Actually, I do it just by looking at it. But the only really interesting mathematical questions to ask have to do with area. Once we have the area, we can then talk about the probabilities of some value falling within a region of the curve. So what's interesting here is not the numbers per se on the y-axis, but the shape of the curve, because those numbers have to be related to the numbers on the x-axis. dx, dy, right? We're looking at derivatives. All right, so now we have to talk about integration. I promise you only hear about it for another few minutes, then we'll leave the topic. So I mentioned before SciPy as a library that contains a lot of useful mathematical functions. One of them is integrate.quad. Well, the integrate part is obvious. It means integration. Quad is telling you the algorithm it's using to do the integration. All of these integrals are going to be actual approximations to the real integral. PyLab is, or SciPy is not doing some clever mathematics to get an analytical solution. It's using a numerical technique to approximate the integral. And the one that's used here happens to be called quadrature. It doesn't matter. All right, you can pass it up to 4 arguments. You must pass it the function to be integrated. That makes sense. A number representing the lower limit of the integration, you need to give it that. A number representing the upper limit, you need to give it that. And then the 4th argument is a tuple supplying all values for the arguments to be except the first of the function you're integrating. I'll show you an example of that on the next slide. And we'll see that it returns a tuple, an approximation to the result, what it thinks the integral is, and an estimate of how much error there might be in that one. We'll ignore the error for the moment. All right, let's look at the code. So we start by importing scipy.integrate. That gives us all the different integration methods. I'm not going to show you the code for Gaussian since I showed it to you a couple of minutes ago, but I wanted you to remember that it takes 3 arguments, x, mu, and sigma. Because when we get down here to the integration, we'll pass it the function Gaussian, and then the values that we want to integrate over. So those will be the values that x can take upon, and that will change as we go from mu minus the number of standard deviations times sigma to mu plus the number of standard deviations times sigma. And then this is the optional 4th argument, the tuple mu and sigma. Why do I need to pass that in? Because Gaussian is a ternary argument, or a function that takes 3 values, and I'm going to integrate over values of x, so I have to fix mu and sigma to constants, which is what I'm doing down here. And then I'll take the 0th value, which is its estimate of the integral. All right, so that's the new thing. The rest of the code is all stuff you've seen. For t in range number of trials, I'm going to choose a random mu between -10 and 10, and a random sigma between 1 and 10. Doesn't matter what those constants are. And then for the number of standard deviations in 1, 1.96, and 3, I'm going to integrate Gaussian over that range. And then we're just going to see how many of them fall within that range. In some sense, what we're doing is we're checking the empirical rule. We're saying, take a Gaussian, I don't care what mu and sigma are, doesn't matter. The empirical rule will still hold, I think. But we're just checking it here. Okay? Well, here are the results. So from ρ equals 9 and sigma equals 6, happen to choose those. We'll see the fraction within 1 fractions when 1.96 and 3. And so for these random mu's and sigmas, you can see that all of them, and you can set them to whatever you want when you get your hands on the code. Essentially what we have is, whoops, the empirical rule actually works. One of those beautiful cases where you can test the theory and see that the theory really is sound. So there we go. So why am I making such a big deal of normal distributions? They have lots of nice mathematical properties, some of which we've already talked about, but all of that would be irrelevant if we didn't see them. The good news is they're all over the place. I've just taken a few here. Up here, we'll see SAT scores. I would never show that to high school students, or GREs to you guys. But you can see that they're amazingly well distributed as along a normal distribution. On down here, this is plotting percent change in oil prices. And again, we see something very close to a normal distribution. And here is just looking at heights of men and women. And again, they clearly look very normal. So it's really quite impressive how often they occur. But not everything is normal. So we saw that the empirical rule works for normal distributions. I won't say I proved it for you. I illustrated it for you with a bunch of examples. But are the outcomes of the spins of a roulette wheel normal? No. They're totally uniform, right? Everything is equally probable. 4, 6, and 11, a 13, 00 if you're in Las Vegas. They're all equally probable. So if I plotted those, I'd basically just get a straight line with everything at 1 over however many pockets there are. So in that case, why does the empirical rule work? We saw that we were doing some estimates about returns, and we used the empirical rule, we checked it, and by George, it was telling us the truth. And the reason is because we're not reasoning about a single spin of the wheel, but about the mean of a set of spins. So if you think about it, what we were reasoning about was the return of betting. If we look at one spin, well, let's say we bet $1. The return is either -1 because we've lost our dollar, or if we get lucky and our pocket happens to come up, it was 36, I think, or 35, I forget which. Okay, but that's all. So if we plotted a histogram, we would see a huge peak at -1 and a little bump here at 36 and nothing in the middle. Clearly not a normal distribution. But what we're reasoning about is not the return of a single spin, but the return of many spins. If we played 1,000 spins, what is our expected return? As soon as we end up reasoning not about a single event, but about the mean of something, we can apply something called the central limit theorem. And here it is. It's actually, for something so important, very simple. It says that given a sufficiently large sample, and I love terms like sufficiently large, but we'll later put a little meat on that, the following 3 things are true. The means of the samples in a set of samples, the so-called sample means, will be approximately normally distributed. So that says if I take a sample, and remember a sample will have multiple examples. So just to remind people, a population is a set of examples. A sample is a subset of the population. So it too is a set of examples, right? Typically. If this set is sufficiently large, certainly 1 is not sufficiently large, then it will be the case that the mean of the means, so I take the mean of each sample, and then I can now plot all of those means, or take the mean of those, right? And they'll be normally distributed. Furthermore, this distribution will have a mean that is close to the mean of the population. The mean of the means will be close to the mean of the population, and the variance of the sample means will be close to the variance of the population divided by the sample size. This is really amazing that this is true, and dramatically useful. So to get some insight, let's check it. To do that, postulate that we have this kind of miraculous die. So instead of a die that when you roll it, you get a number 1, 2, 3, 4, 5, or 6, this particular die is continuous. It gives you a real number between 0 and 5, or maybe it's between 1 and 6. Okay? So it's a continuous die. What we're going to do is roll it a lot of times. We're going to say how many die, and then how many times are we going to roll that number of die. So the number of die will be the sample size. Number of dice will be the sample size. And then we'll take a bunch of samples, which I'm calling number of rolls. And then we'll plot it, and I'm just saying, choosing some bins and some colors and some style and various other things just to show you how we use the keyword arguments. So actually I said num rolls is the number of trials, but it isn't quite that, because I'm going to get the number of trials by dividing the number of rolls by the number of dice. So if I have more dice, I get to have fewer samples, more dice per sample. All right? Then we'll just do it. So it will be between 0 and 5, because random.random returns a number between 0 and 1, and I'm multiplying it by 5. And then we'll look at the means, and we'll plot it all. Again, we're playing games with weights just to make the plot a little easier to read. And here's what we get. If we roll 1 die, the mean is very close to 2.5. Well, that's certainly what you'd expect, right? It's some random number between 0 and 5. 2.5 is a pretty good guess as to what it should average. And it has a standard deviation of 1.44. That's a little harder to guess that that's what it would be, but you could figure it out with a little math, or as I did here with the simulation. But now if I roll 50 dice, well, again, the mean is close to 2.5. It's what you'd expect, right? I roll 50 dice, I get the mean value of those 50. But look how much smaller the standard deviation is. More importantly, what we see here is that if we look at the value, the probability is flat for all possible values between 0 and 5 for a single die. But if we look at the distribution for the means, it's not quite Gaussian, but it's pretty close. Why is it not Gaussian? Well, I didn't do it an infinite number of times. Did it quite a few, but not an infinite number. Enough that you didn't want to sit here while it ran. But you can see the amazing thing here that when I go from looking at 1 to looking at the mean of 50, suddenly I have a normal distribution. And that means that I can bring to bear on the problem the central limit theorem. We can try it for roulette. Again, I'm not going to make you sit through a million trials of 200 spins each. I'll do it only for fair roulette. And again, this is a very simple simulation. And we'll see what we get. And what we see is it's not quite normal again, but it definitely has that shape. Now, it's going to be a little bit strange because I can't lose more than 1, right, if I'm betting 1. So it will never be quite normal, right, because it's going to be truncated down on the left side. Whereas the tail can be arbitrarily long. So again, mathematically, it can't be normal, but it's close enough in the main region where most of the values lie that we can get away with applying the empirical rule and looking at answers. And indeed, as we saw, it does work. So what's the moral here? It doesn't matter what the shape of the distribution of the original values happen to be. If we're trying to estimate the mean using samples that are sufficiently large, the CLT will allow us to use the empirical rule when computing confidence intervals. Even if we go back and look at this anomaly over on the left, what do you think would happen if I, instead of had 200, had, say, 1,000? What's the probability of the average return being -1 of 1,000 bets? Much smaller, right, than for 100 bets. To lose 1,000 times in a row is pretty unlikely. So to get all the way to the left is going to be less likely, and therefore the thing will start looking more and more normal as the samples get bigger. All right. And so we can use the CLT to justify using the empirical rule when we compute confidence intervals. All right, I want to look at one more example in detail. This is kind of an interesting one. You might think that randomness is of no use for, say, finding the value of pi, because there's nothing random about that. Similarly, you might think that randomness was of no use in integrating a function. But in fact, the way those numerical algorithms work is they use randomness. What you're about to see is that randomness, and indeed things related to Monte Carlo simulations, can be enormously useful even when you're computing something that is inherently not random, like the value at pi here. And we won't ask you to remember that many digits on the quiz, in the exam. All right, so what's pi? Well, people have known about pi for thousands and thousands of years. And what people knew was that there was some constant, we'll call it pi, it wasn't always called that, such that it was equal to the circumference of a circle divided by the diameter. And furthermore, the area was going to be pi r squared. People knew that way back to the Babylonians and the Egyptians. What they didn't know is what that value was. The earliest known estimate of pi was by the Egyptians on something called the Rhind papyrus, pictured here. And they estimated pi to be 4 times 8 over 9 squared, or 3.16. Not so bad. About 1,100 years later, an estimate of pi appeared in the Bible, King 723. Didn't say pi is, but it described, I think this was a construction of King Solomon's temple. He made a molten sea 10 cubits from one brim to the other. It was round, i.e. it was a circle. His height was 5 cubits, and a line of 30 cubits did compass it round about. Well, if you do the arithmetic, what does this imply the value of pi to be? 3. And I'm sure that's what Mike Pence thinks it is. About 300 years later, Archimedes did a better job of it. He estimated pi by constructing a 96-sided polygon. There's a picture of one. It looks a lot like a circle. On the left is one with fewer sides. And what he did is he then, since it was a polygon, he knew how to compute its area or its circumference, and he just counted things up. And he said, well, pi is somewhere between 223 over 71 and 22 over 7. And that turns out to actually, if you take the average of that, be a really good estimate. 2,000 years after Archimedes, the French mathematicians Buffon and Laplace proposed finding the value of pi using what we would today call a Monte Carlo simulation. They did not have a computer to execute this on. So what they proposed started with this mathematics. They took a circle and inscribed it in a square of 2 units of whatever it is per side. And therefore, we know that the area of the square is 2 times 2, or 4. We know that the area of the circle is pi r squared. And since we know that r is 1, because that's the square it's inscribed in, we know that the area of the circle is exactly pi. What Buffon then proposed was dropping a bunch of needles at random, kind of like when Professor Grimson was sorting things, and seeing where they land. Some would land in the square, but not in the circle. Some would land in the circle. You would ignore any that landed outside the square. And then they said, well, since they're falling at random, the ratio of the needles in the circle to the needles in the square should exactly equal the area of the square over the area of the circle. Exactly if you did an infinite number of needles. Does that make sense? Now, given that, you can do some algebra and solve for the area of the circle and say it has to be the area of the square times the number of needles in the circle divided by the needles in the square. And since we know that the area of the circle is pi, that tells us that pi is going to equal 4 times the needles in the circle. That's 4 is the area of the square, divided by the number of needles in the square. And so the argument was you can just drop a bunch of these needles, see where they land, add them up, and from that you would magically now know the actual value of pi. Well, we tried a simulation one year in class, but rather than using needles, we had an archer and we blindfolded him, so he would shoot arrows at random, and we would see where they ended up. There's a video of this here if you'll want to see it. I'm going to play only the very end of the video, which describes the results.
Maybe we should just use Python to build a Monte Carlo simulation instead.
So that's what happened. After it was all over, Anna came up and gave me some sound advice. Yeah, I was very proud of that particular shot with the apple. I had hoped the student would put it on his or her head, but no one volunteered. That was not done blindfolded. Any rate, so here's the simulation. So first we have throwing the needles. For needles in range 1 to number of needles plus 1, we're going to choose a random x, a random y, and we're going to see whether or not it's in the circle, and there we'll use the Pythagorean theorem to tell us that. All right? And we'll just do this, and then we're going to return exactly the formula we saw in the previous slide. Now comes an interesting part. We need to get an estimate. So we start with the number of needles and the number of trials. For t in range number of trials, we'll get a guess by throwing number of needles, and then we'll append that guess to our list of estimates. We'll then compute the standard deviation, get the current estimate, which will be the sum of the estimates divided by the len of the estimates, just the mean of the estimates, and then we'll print it. All right? So given a number of needles and a number of trials, we'll estimate pi, and we'll give you the standard deviation of that estimate. However, to do that within a certain precision, I'm going to have yet another loop. And I'm showing you this because we often structure simulations this way. So what I have here is, well, the number of trials, which is not so interesting, but the precision. I'm saying I would like to know the value of pi, and I would like to have good reason to believe that the value you give me is within 0.005, in this case, of the true value. Okay. Or maybe more precisely, I'd like to know with a confidence of 95% that the true value is within a certain range. So what this is going to do is it's just going to, I should have probably used 1.96 instead of 2, but oh well. It's just going to keep increasing the number of needles, doubling the number of needles, until it's confident about the estimate, or confident enough. All right, so this is a very common thing. We don't know how many needles we should need, so let's just start with some small number, and we'll keep going until we're good. All right, what happens when we run it? Well, we start with some estimates. When we had 1,000 needles, it told us that pi was 3.148, and standard deviation was 0.047, et cetera. So a couple of things to notice. One, are my estimates of pi getting monotonically better? You'd like to think as I add more needles, my estimates are getting more accurate. So that's question one. Are they getting more accurate? Not monotonically, right? If we look at it, where are they getting worse? Well, let's see. 3.148. Well, 3.13 is already worse, right? So I double the number of needles and I get a worse estimate. Now the trend is good. Right, by the time I get here, I've got a pretty good estimate. So overall, as I look at larger samples, a bigger subset of the population, my estimates are trending towards better, but not every time. On the other hand, let's look at the standard deviations. What we see here is that the standard deviations are indeed getting monotonically better. Now, there's nothing mathematical guaranteeing that, right? Because there is randomness here. But I'm increasing the number of needles by so much that it kind of overrides the bad luck of maybe getting a bad random set. And we see those are getting better. So the important thing to see here is not that I happen to get a better estimate, but that I know more about the estimate. I can have more confidence in the estimate because it's closing in on it. So the moral here is it's not sufficient to produce a good answer. I've said this before. We need to have reason to believe that it is close to the right answer. So in this case, I'm using the standard deviation and say, given that it's gotten quite small, 2 times 1.96 times 0.002 is indeed a small number. I could make it smaller if I wanted. I believe that I have good reason to believe I'm close to the right value of pi. Everyone agree with that? Is that right? Not quite, actually. It would be nice if it were true, but it isn't. So let's look at some things. Is it correct to state that 95% of the time we run this simulation, we'll get an estimate of pi between these two values? I don't expect you to do the arithmetic in your head, but the answer is yes. So that is something we believe is true by the math we've been looking at for the last 2 lectures. Next statement. With the probability of 0.95, the actual value of pi is between these two things. Is that true? In fact, if I were to say with the probability of 1, the actual value is pi is between those two values, would it be true? Yes. So they're both true facts. However, only the first of these can be inferred from our simulation. While the second fact is true, we can't infer it from the simulation. And to show you that, statistically valid is not the same as true, we'll look at this. I've introduced a bug in my simulation. I've replaced the 4 that we saw we needed by 2. Easy kind of mistake to make. And now if we go to the code, well, what do you think will happen if we go to the code and run it? We'll try it. We'll go down here to the code. We'll make that a 2. And what you'll see as it runs is that once again, we're getting very nice confidence intervals, but totally bogus values of pi. All right, so the statistics can tell us something about how reproducible our simulation is, but not whether the simulation is an actually accurate model of reality. So what do you need to do? You need to do something like a sanity check. So here you might look at a polygon and say, well, clearly that's a totally wrong number. Something is wrong with my code. Okay, so just to wrap up, what we've shown is a way to find pi. This is a generally useful technique to estimate the area of any region R. You pick an enclosing region, call it E, such that it's easy to estimate the area of E, and R lies within it. Pick some random sets of points within E. Let F be the fraction that fall within R, multiply E by F, and you're done. So this, for example, is a very common way to do integration. I promised you we'd talk about integration. So here's a sine of x. If I want to integrate the sine of x over some region, as done here, all I need to do is pick a bunch of random points, red and black in this case, and look at the ratio of one to the other. So showing how we can use randomness to, again, compute something that is not inherently random. This is a trick people use over and over and over again when confronted with some situation where it's not easy to solve for things mathematically. You just do a simulation, and if you do it right, you get a very good answer. All right, we'll move on to a different topic on Wednesday.
Okay, that was also really math heavy. It was an interesting lecture. I guess the part on where like he used like a large enough sample set, and then the central limit theory or the proof of that was pretty cool. If you have a sample size that's like large enough, it's gonna follow like some sort of normal distribution where you can have the whole 95% confidence interval rate that you will get that value even though all the probability of each value occurring is equal, right? But on a large sample set somehow it works out, right? And then also towards the end, it was a thing that was pretty obvious that you can have if something is probabilistically true, it doesn't necessarily mean that the actual result is true just because of the way sample size works, just because of the way the experiment works, right? So my experiment could be wrong, and I might have a high enough confidence interval rate, but that high confidence interval rate is for the wrong value, not the right value that we want. So doing a sanity check is pretty important. With that being said, I'm gonna finish P set 3 right now. I'm gonna go and then I'm gonna work on P set 3 and try to finish the whole P set. I'm gonna run to the bathroom pretty quick. So I got the test cases, well, the actual test file to be working, so yeah, I can run that. There's a lot of test cases that I'm failing at, of course, because my code isn't fully done yet, and I'm pretty sure I made like lots of errors, which I did problem 1, right? Yeah, so we can look into those errors, and then there's a lot of errors. Some of them are okay, like get robot direction, set robot direction. Still a lot of errors, so we will look into those, and then we'll try to fix problem 1 before we actually dive into problem 2. I don't think so that's gonna work. Yep, that was just a bad idea. Trust publisher installed. it's enabled. There we go. Okay. So yeah, and then we're gonna implement problem 2, which is implementing empty room and furnishing, so subclasses of room, and then subclasses of robot, and then simulating, so to simulate an experiment, and then implementing another subclass of robot, and then creating another simulator. So it's a long enough piece set, but let's see. I think it's impossible, right? Before that, let me do a quick break. start. Display capture, yep. And then video capture. I mean, I can do video capture, suppose. Okay. So actually I can, yeah, I mean, there's a problem set alone should be fine though, right? Okay, so let's try to whatever we did, let's try to test everything out, make sure our first problem set actually works, and then we can tackle problem 2, right? Before that, let me set a timer for 2 hours. There we go. Okay, it's 9:30 right now. It's snowing outside. Okay, tests. Okay, 43 tests. So what are the functions that we implemented? So we implemented init for position, right? We implemented get new position. Oh, never mind. We implemented init for the rectangular room, clean tile at position. Okay, so this is shouldn't be an error, but clearly there is. So let's think about it. Hide data among self rec. Yes, we declared a rectangle, a dictionary. We have our width and height, and then for each of those we have a specific dirt amount, right? So actually, let's see the error. Key error. Okay. So there's a key error. So why would there be a key error? So we do position pos dot get underscore x and pos dot get underscore y, and then we do dirt equals self dot get underscore dirt amount. So this is where the key error is happening. So get dirt amount, what are we doing? We're doing self dot rec assumes this already assumes that m and n are valid tile inside the room. M is an integer and n is an int. Okay, I think I understand. There was something, yep. So position, position represents 2 floats from 0 to width and 0 to height, right? And so each robot, so rectangular room, so exactly, so each rectangular room is gonna be an ordered pair of integers, right? So we can use, there was yeah, math.floor x, right? So we can definitely use that. So if we go right, x comma y equals math.floor x comma math.floor y. This should be good. Never mind. Wrong file. Test it. Oh, no. It should be better. Yeah, I mean, it definitely decreased number of errors, I think. Let's see. So, clean toilet position removes all dirt. So, a few errors here. So, let's see. Okay. Let's go here. Is an x plus random y dot on key error. So there's another key error happening. For some reason. Let's see. Even though I did the whole math.floor thing, it's still doing a key error when I call self.get underscore dirt amount with x comma y. Even though it shouldn't. The output resolution is horrendous. Okay, so for some reason 0,3 is having a major key error, right? Yeah, all of them is just key error 0,3. So let me try to see if there's something that can't be 0, like that. Yeah, I mean, it has to be greater than 0. So if this is 1, then this is gonna have a 0, 0 coordinate, right? So let's see how there's gonna be a value over here, self.rec. X comma y get pulse dot get underscore x, pulse dot get underscore y, math dot floor x, math dot floor y, get underscore dirt underscore amount x comma y. After calling floor, and then on get underscore dirt, all I'm doing is returning the value, correct? And then in this case I'm assigning that dirt amount to I comma j. It's interesting, but there's still a key error of 0 comma 3. Try to think why. was a test case that I'm failing at. Nope. Test case that I'm failing it is test underscore at position pos to pos 0. In particular, it calls that function. So and I create my rectangular blue with 3 width, 4 height, and dirt amount of 1. So this should call my init function. My width is greater than 0, my height is greater than 0, and my dirt amount is definitely greater than equals 0, right? So this should create a rectangle, assign each width and height to the variables, and then loop over height, loop over width, go from the value, make the dictionary, right? Create the dictionary, and then for that width comma height, clean tile underscore at position, okay, test dot position, so x plus random dot random plus y plus random dot one data amount. What's for tile? Okay. So some amount 0 plus some amount, then 1 plus some, 2 plus some amount, whatever value we get, we have to round that down. That's what we do. We round it down. Did I save it? I think I did save it. And then the only thing it makes sense for like here is it happens when I'm doing the init thing, because otherwise for some reason 0, 3 isn't a value. Now let's see. So it should be a value because this is 4. So this is gonna go up to but not including 4. The second one is the height. Wait, so this is the height. So height is the second parameter passed in. So it should be this width, and then that doesn't make sense to me, but it looks like that's what's happening, right? Yeah, the errors definitely is 14 failures and 17 errors. That doesn't fail. And not implemented is fine. think so. Simulations started yet. We didn't do simulations yet. This is the room of the robot, right? So let's see. Okay. 00 was marked clean. Okay, let's try to get is style cleaned. Is style cleaned? That's true. Is greater than the number of dirt is we're doing what about dirt that is there right now. Minus should be capacity, right? Minus capacity. Clear. Run it. 12 failures and 17 errors. Okay, I mean a lot more okay right now, right? A lot more okays. Position in room. A lot of okays actually. It's just P2, so P2 is I'm not doing P2, right? Simulation, 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 simulation. Looks like they're all just simulations. I don't know. I think all the code for problem one is okay. Might be wrong. Let's see. It says it's B5, 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 B5. Because yeah, for robot, it shouldn't be because I didn't change anything for robot, right? B5, B5, B5. Yeah, B1. This is B5, but B1. This is false. Okay. Is position in room. Okay, is position in room. So we have to basically if we do math.floorx, math.floorY, right? is definitely the way to go. KOS failures. Let's see now. This is p5, 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 p5. That's p1, right? Okay, so it's still not correct. How many p1 errors do we have? That's p5, 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 p3, 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 p2, p2, p2. Yes, I'm guessing we have only one p1 error, and I'm gonna just check over the code for my robot class, see if it's okay or not. Might not be okay, right? Okay, so it's just, yeah, I'm pretty sure these are all correct. Yep, because these are very basic functions, right? So okay, so the only thing that's not working right now is it is, where did it go? It is in room, right? Which, I mean, it should be a simple function, but I think I have a logical error or something. Test is position in room. Okay. Test is position in room. Okay, so width comma height moderate amount. Width is 3, height is 4. Okay. So we create a room, right? Okay, solution room, and then we loop over it. It's crazy that I'm not seeing the actual value, so I'm just seeing the print statement. I mean, I guess that's fine. I mean, should be able to debug something. True not equals false position. 0 0.0 or 0 0.0 is incorrect. Expected true. Got false. Okay. If position is in the room, right? So this is fine. So maybe I have some misunderstanding on what should be is in room, right? Okay. So this ain't working, right? So y is gonna wait for 0, and then 0, 0, 0, 0. So if that is gonna be that position is in the room, right? So we call that is position in room, right, with 0, 0 technically. Since it can be 0, it would equal to nope. And now there you go. Clear this. And the test cases: 11 failures, 17 errors. Maybe passed it, right? It was 12 last time, right? This is PS5, 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 P5, P5, 5, 5, 5, 5, 40, 40, 5, problem 3, problem 3, problem 2, and then it looks like all the, yep, it looks like all the problem 1 things are okay. I dare say, right? But let's look at the robot code. So initial robot with the given speed and cleaning capacity in the specified robot, initial random direction, random position in the room. So room dot get random position. So the reason why this code is working even without any conversion, because I totally forgot about that, is because it inherently expects room dot get random position to give like the correct position inside a room, i.e. integers, right? And the rest of them are pretty simple. Okay, now problem 2. We're done with problem 1. Like officially done. This previous problem we implemented the rectangular room plus. Now we wanna consider additional kinds of rooms with furniture, furnished rooms, and rooms without furniture. These rooms are implemented in their own classes and have many of the same methods as rectangular room. Therefore, we'd like to use inheritance to reduce the amount of duplicated code by implementing furnished room and empty room as subclasses of rectangular room according to the image below. Fair enough. Think about how the methods you need to implement differ for the two classes and how you can use the methods already implemented in the parent class. Note failure to take advantage of inheritance will result in deduction, of course. Additionally, be careful in determining whether a position is valid. Recall that in the case of furnished room, a robot cannot be in a position in a tile that has a furniture. Finally, in the furnished class, we have implemented the add furniture to room method. To add a rectangular furniture piece into the room for you, you do not need to call this method. Provided test code will call it for you. Do not change this method. Okay. Complete the empty room and get and furnished room class of implementing the methods. Read the code we have provided carefully to understand how furnished room differs from empty room and rectangular room. How are the furnished tiles stored? Remember, the tiles are represented using ordered pair of integers, but a robot's position specified as floats. Be careful converting between the two. We recommend using math.floorx to always round down when converting to ensure that positions are always in the room. Okay. Doesn't look like the worst. I don't know why I'm clearing it. It's already cleared. Okay, let's do empty room. returns an integer, the total number of tiles in the room. So if I'm not wrong, get num tiles. Okay, return total number of tiles in the room. So that I need to create here. So this represents a rectangular room with no furniture. So I have my hopefully I have my rectangular room in it, right? Hopefully. So if I do self dot so what I was gonna do is total number of tiles is basically gonna be the length of the dictionary, right? So if I do something like return len self dot rec, that is the total number of tiles, right? Because in the end, I mean, that's what I'm doing. I can do width times height as well, but same thing towards the end. Well, can you call the dictionary? Finding length of dictionary in Python. There is, yeah, there is the len operator works. Okay. Is position valid? Not sure if boss is in your room. So was this done? Is position okay? So anything that's here. So for this one, isn't it just return self dot is position in room pause, right? Because then what are we passing to? Is position in room. Yeah, we're just passing in position, right? And if it's valid, then that means that position is in room, because this is an empty room. This is not a furnished room, so a valid random position inside the room. Okay, this is interesting. So what can we do? Okay, let's see. X comma y equals width times random dot random, right? And actually self dot width times random dot random and self dot height times random dot random. X comma y equal math dot floor x comma math dot floor y, and then return position x comma y. Okay, so that should be empty room done. Now we have furnished room. So furnished room should be slightly harder than empty room, but not that much in my opinion. And then that's problem 2 done. Then we can move on about maybe problem 3, we're like more than halfway done. Okay, that's from the test cases for empty room though, right? Failures 11, errors 15. Okay. Ooh. Simulation A, that's problem 5. Problem 5. 5. 5. 5. 5. 3. 3. 3. There we go. This is for furnished. FR is for furnished. ER. Okay, get random position. Module random has no attribute. A little bit of typo. There we go. Feel like this should work. Let me run it. Failures 11, errors 12. Problem 5, 5, 5, 5, 5, 5, lot of problem 5, 5, 3, furnished room, furnished room, furnished room. Yep. Oh, is this that's FR, right? Yep, that's not here. So empty room works. Let's try to do furnished room. Add furniture to robot. Add furniture to room has been done. Add furnished as stored as x comma y. Okay. So let's try to actually read through the code. Subclass of rectangular room. Furnished room has also a list of tiles which are furnished. Okay, so that's just a list, an empty list for now. Adds a rectangular piece of furniture to the room. Furnished tiles are stored as x comma y tuples in the list furniture tiles. Okay, furniture locations and size is randomly selected. Width and height are selected so that the piece of furniture fits within the room, doesn't occupy the entire room. Selected by randomly selected the location of the bottom left corner of the piece of furniture. The entire piece of furniture lies in the room. Okay. Is tile returns true if tile m comma n is furnished. Fair enough. I feel like we can do return m comma n in self dot furniture underscore self. There we go. Returns true if position is furnished and false otherwise. Isn't it basically like the first one? So we get x comma y right equals pos dot get underscore x right comma pos dot get underscore y right. Those are the methods, right? Position. Yeah, get underscore x and get underscore y. So I mean that can be float. So I guess the only thing that we can change is x comma y equals math dot floor x. I don't know if this is correct though. I mean there, but it won't hurt us, because if we are given integers only, then well, it's gonna turn it into an integers. So return self dot is underscore tile underscore furnished x comma y. Okay. Returns true if pause is in the room and pause is unfurnished, false otherwise. Okay. Yeah, I mean, I can do this. Return self dot rectangular room dot closed. Okay. Rectangular room is underscore position valid, right? We'll pass in self and then we'll pass in pause, and alongside that we can do self dot is position furnished, and we'll pass in the position. There we go. Get num tiles returns an integer, the total number of tiles in the room that can be accessed. Okay, tiles in the room that can be accessed. So okay, so this is basically gonna be rectangular room dot get num tiles, right? We need to pass self, right? Yeah, minus length of self dot furniture tiles. Return that. There we go. Okay. Get random position. A valid random position inside the room and not in a furnished area. So let's see. So there is position valid, right? That takes n up, so we can do pause equals, is there a get random position? There is one for empty room, but that doesn't take an empty room, and for rectangular room there isn't one. I mean, I have to implement one for this. So the same code for this. Suppose a lot of it is going to be, I'm just gonna copy and paste it. There's just one caveat here, right? Okay, so instead of this, while x comma y, so as long as this is in self, or I can just use it is while is self dot is underscore tile underscore furnished, right? While self dot is underscore I feel like this just looks better if I used this for x comma y. So while this is true, we're gonna recalculate the value of x comma y. Oops. So we recalculate the value of x comma y, and this is, if this is ever false, right? So is style underscore furnished, right? So if this is ever false, then we return position x comma y. So hopefully this works. I mean, let's see. Okay, we have 11 failures and 10 errors, so guess we're getting closer. P5, 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 still P5, P5, P5. Holy, okay, P3. Okay, so there's definitely something is wrong with this positioner survival. Apparently that's not implemented. I definitely implemented that, but apparently it's not. Okay. Did I implement it to the wrong class? Nope. I don't know why it would say that. What does this say? Yeah, random position. I also implemented this, but apparently it's not implemented. Apparently this is not implemented as well. So maybe I forgot to save it, right? So Control S. Maybe now if I run it, it still shows errors 10 and failures 11. So I think that's the same, right? Yeah, it says not implemented error, which doesn't make sense because I definitely implemented it. Let's see what's happening inside the test code. So it's not ER, it's FR, right? FR, there we go. And the code is get underscore num tiles. That's the first one. So it's implemented, alright. What is it? Get num titles. Yeah, I mean, I don't know, man. It looks implemented to me. not implemented error is kind of crazy. See, so rectangular room dot get underscore numbers. It is running this code, but once it runs this code, I'm guessing this part of it implemented in rectangular. Okay, so I didn't implement it here, so it's supposed to be implemented only in the subclass. Okay, so what we can do is self dot, well, len of self dot rec, right? Whatever that is, minus len. Okay, so definitely decreased in an error, so there's that. Okay, I mean, still something. Get random position for furnished room. Okay, for furnished room. So where is get underscore? Okay, so we have get underscore position, return rectangular room is position valid. What? That is crazy. So what's happening here is because I know that I didn't implement it for rectangular rule, right? So calling is self underscore tile is furnished, and then this is doing return m comma n and self dot furniture underscore tile. So it's I don't know. It's not doing position, it's doing tile. This is the underscore random position for furnished room. So there's that, and then there's this position valid, which also has the same not implemented error. So let's see for the random position. Get underscore random position. Okay. So it creates a room, a furnished room to be exact. And then for 5,000 it does room dot get underscore random position. Okay. So pretty self-explanatory. Get underscore random position. So what am I doing in get underscore random position? I'm doing x comma y self dot width. So I'm doing math dot floor, and then I'm calling the function, and then I'm doing the same thing over and over in the function. And then in the end, I return position x comma y. So where is it getting the whole assert true? Is underscore position valid? So it calls. Is there something called rectangular room is underscore position valid? That might not be the case. Oh, hell. If pause in the room Oh yeah, is position in room. That's not a bad method to use. Position in room, and that also takes into parameter. That takes a position, right? Mm, yes, it does. Maybe, just maybe. Error cells. We decrease the number of errors by a lot. This might be it. Maybe we put here. P5, P5, P5. Okay. A lot more P5, but so I think is position underscore valid is where the errors are happening. I feel like if we can fix that, then we can fix the get underscore random position. That's gonna be okay. So is position underscore valid? Let's try to see what's happening. So if position is furnished, right? So this should be not. Maybe this should fix it. 7 errors still happening. Ay. I mean, failures is the main thing, right? Not errors, technically. I didn't check if the number of failures decreased. Kind of decreased. P3. Hey, we should be chilling. I don't think so there's any furnished room problem. P5, 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 P5. Yeah, I think that's all the problem done. Let's see. P1, everything works, right? P2, looks like everything works. And yeah, it's from P3 where we're getting errors, and P5, of course. There's a lot of errors in P5, but yeah, problem 2 is basically done. So we can start doing problem 3, which is standard robot, and then simulating a time step. And problem 4 is implementing a faulty robot when we're creating the simulator. I'm gonna have to do a quick bathroom break before that, but I'll be back in like 5-10 minutes. Okay, so okay, we're back. Let's try to do problem 3, standard robot and simulating a time step. Okay, so each robot must also have some code that tells it how to move powder room, which will go in a method called update and position and clean. Okay. Ordinarily, we would consider putting all the robots method in a single class. However, later in the problem sets, we'll consider robots with alternate movement strategies to be implemented as different classes with the same interface. Okay, these classes will have a different implementation of update and position and clean. Okay, but are for the most part the same as the original robots. We will again make use of inheritance to reduce the amount of duplicated code. Fair enough. We've already refactored the robot code for you into 2 classes. The abstract robot class you completed above, which contains general robot code, and a standard robot class inheriting from it, which contains its own movement strategy. The movement strategy for standard robot is as follows in each time step. Calculate what the new position for the robot would be if it moved straight in its current direction at its given speed. If that is a valid position, move there and then clean the tile corresponding to that position by the robot's capacity. Okay, the position is valid if it is in the room, and if it is unfurnished, do not worry about the robot's path in between old position and the new position and whether there is furniture in that path. So we don't care about furniture. Well, as we're going through the path. Otherwise, rotate the robot be pointing in a random new direction. Don't clean the current tile or move to a different tile. We have provided the get underscore new position method of the position class, which you may find useful in implementing this. It computes to return the new position for the current position object after a single clock tick has passed with the given angle and the speed parameters. Read the doc string for this method for complete information. Complete the update position and clean method of standard robot to simulate the motion of robot during a single time step as described above in the time step dynamics. Before moving on problem 4, check that your implementation of standard robot works by uncommenting the following line under your implementation of standard robot. This will test if your robot moves correctly in empty room. When you've checked that your robot moves correctly, make sure to comment out. The test file will display a 5x5 room implemented empty room and a robot as implemented in standard robot. Initially, all dirty tiles are marked as black. As the robot visits each tile and clean the tile by its given capacity, the color of the tile changes from black to gray to white, with white meaning completely clean. Okay. Make sure the robot moves around the room. The tiles get lighter from black to white as shown below. Each time when your robot traverses, the simulation terminates when the robot finishes cleaning the entire room. Make sure your robot doesn't violate any of the simulation specifications. Example, your robot should never move to a position outside of your room. It should never clean the tile if it also had to choose a new direction, etc. You should also test if your robot moves correctly in a furnished room by uncommenting the following line. Okay. You should not have to change the implementation of update position and clean for this to work. Remember to comment the lines out when you are done testing. Do not worry if it appears your robot is cutting corners as it cleans, as long as the final position in each step is moved on a furnished red tile outside the room. Comment out the line. Okay. So lots of things to do, but it's not unreasonable. So let's get going. Okay, standard robot. Clear the terminal. Okay. A standard robot is a robot with a standard movement strategy. Okay, at each time step, a standard robot attempts to move in its current direction. When it will hit a wall or a furniture, it instead chooses a new direction randomly. Simulate the race passage of a single time step. Move the robot to a new random position. The new position is invalid. Rotate once to a random new direction and stay stationary, and clean the dirt on the tile by its given capacity. Should be interesting. So it's just one method that we're gonna do. Okay, so that first we need to have our new random position, right? So some random position. This takes in robot. Suppose we can get yeah, so let's do this. Self.room equals room. Okay, so I have my rectangular room object. Nice. So I can reference all the methods that I've defined within that. So this makes it significantly simpler. I'm just gonna say r self dot get dot room dot get underscore random random position, right? Okay, so we have r here. It should be a valid position. Well, yeah, because it's not a oh, I see. So never mind, my understanding was bad. So at first our robot is already at some random position. Yeah, it's within a valid random position. So let's try to since this is larger than the usual file, let's try to comment some steps out. So what are we gonna do? How do we simulate whatever's happening in here? Let's read the problem set a bit more. So at first we need to see where the robot would go given its current speed and direction. So we can get robot position, direction, then is there anything for speed? Okay, so at first we do get robot position, speed, and directions. So pause, comma, speed, comma, directions equals self dot get robot position, self dot speed, right? And then self dot get robot direction. Okay. And then we do is get new position. So for that, we'll go to position class. Yeah, there's new position. So angle and speed, right? But before that, does it clean the position that where it started at, right? Because what I'm thinking is when, so let's say if we have the robot starting out, right? If it's in the center, does it clean the center and then move to a new position? I don't think so, right? So at first we need to get the new position. So pause equals pause dot get new position, right? Position. Pause the method. I get into the angle and speed. So angle, which is directions, and speed. Okay. We'll now check if position is valid. So the way we do that is we have way too many methods. So it's of a single time step, so we don't need to do multi-time, we can do single time, so it's just one time, right? Okay, so just rotate the robot. Okay, so what do we do here? Is position valid, right? Self dot room dot is underscore position underscore valid, pass in pause, this is true, then we change it, right? We do was defined up here. Clean tile at position, right? So self dot room dot clean underscore tile underscore at position. Oh my god, I keep forgetting the method signatures. It takes position and then capacity. Position and then capacity. So capacity is called capacity, self-dot capacity. So it's position and capacity. Okay, so position and then self dot capacity, right? Otherwise we change the robot's direction, else we just change the direction. So we just rotate the robot. Don't clean the current tile or move to a different tile. Okay, so was that implemented somewhere? I'm forgetting. I swear I remember doing 360. Yeah, this is okay. So else, I mean, I'm gonna write proper code and I'm gonna do 360 times random dot random, right? And then actually reference the method that I wrote. So set underscore robot direction, right? Yeah, so self dot set underscore robot direction, and then pass in the angle, and this should be it. Let's do the empty room at first, and then we'll do the furnished room. I don't know why I cleared it, but let's see. Clearly, yeah, nothing's working here, is it? Ay, ay, ay. Okay, so if I'm not right, this is just one instance of a single time step. So I'm guessing the loop should be when we're calling the function. Let's see. Simulation problem 6. Show plot. Okay. Ay, ay, ay. Clearly, even if I run it, I mean, it's just, yeah. Where is this pointing? It's not. Damn. Where am I going wrong? Oops. Think. Even the beginning, the robot is starting at a weird position, right? Which it shouldn't. Sure, we get room dot get underscore random position, right? So that is a valid position. Let's run the test cases. Let's see where we're at. I. Hey, let's comment that line out. Wait. Okay. Now let's run the test cases. Let's see. Error 6, failure 12. P5, 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 P5. Is there any problems at 3? There is. Okay, okay. So P5, 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 P3. Okay, so there's one P3 problem clearly happening. What is the problem? Update position clean standard robot. PS2. Robot dot get in the robot position. False is not true. Robot position is updated incorrectly by update position. Expected PS3. So clearly there's something wrong. I'm not updating the position. So I need to update the position. That's what's not showing up. Set robot position, right? Self dot set underscore robot position. Pause. Okay. Maybe you'll work now. Yes, sir. I mean, it's moving around. It's changing direction. It's just it's not cleaning anything. So clean tile at position pause comma self lift capacity. There's nothing wrong with that, right? Oh, it is there. Update position. So self dot room. So whatever I'm doing self dot room. So it's going through the robot's internal room attribute. And then in there I'm doing clean tile at position. So it should work maybe. Self dot room dot, and it's changing. It changes the room itself, right? It's yeah, it's a mutable method. But apparently it's my movement's fine. It's just that my it's 0% clean, like it's not cleaning at all for some reason. The movement simulation is fine though. But yeah, this is just not, it's just not cleaning at all for some reason. Let's see. It looks cool though. Okay, 6 errors. P5, 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 P3, yeah. Marked one or yeah, exactly. It's not cleaning, no. For some reason. Don't know why. It is, I'm doing self.clean tile position, right? Or it's not assigning, I mean, it should assign that position to be clean, right? Or whatever. It's just not happening. Yeah, but like when I call is, I don't know, is clean tile position. It is mutating the object, right? So I'm going self.room, and inside self.room, basically self.room.rec, right? It is mutating that that dictionary. Still not cleaning though. Ugh. Ay. And then it's cleaning by the capacity. Self.capacity, right? Let's test something out. Okay, P3, empty room. I think 1.0 is the let's see the init method for robots. 1.0 is the speed and 1 is the capacity. Okay, that's how we're creating the robots, right? Current Arcoma robots, boundary conditions. So this is fine. Boundary condition is fine. It's the clean robot that's the problem. It says the furnished room, just for the sake of it. I mean, the movement is fine. It's just the cleaning of the tile itself. It's not moving towards the furnished rooms. It's just not cleaning anything for some reason. Which should be the simplest thing to do, right? Oh, fuck's sake. Ugh. Nope, not clear. Clear this. Why are you not working? Mm. Mm. It's just I'm having a hard time debugging this. It's 22 degrees right. Yeah, I'm still having a hard time debugging this. Because it the code seems okay to me. I'm gonna be real. Because we're calling the method right clean tile acquisition, so it should clean whatever the tile is and then modify it accordingly. And I don't think so. Using a dictionary is a bad thing for that, right? And we're given the freedom. we are officially stuck, aren't we? Trying to think of what to do. Drop my phone, it's fine. Let's see if there's any debugger in here, because that might help me. Although I can tell that it's gonna be a bitch to debug this, and no, not GitHub. Let's the phone still works. By debug in VS Code, right? So add a breakpoint. Press F5. Python debugger. Python file. Yeah, this is Python 3.5. So that's not gonna work. Oh, thought I hooked something up, didn't I? But it's just not gonna work. So we're gonna have to do manual debugging, but I genuinely don't know what's wrong with it. Aside from like reading the code that was already given, which I guess visualize.py. Can help me, I suppose. So this is how they're getting the color, right? Yeah, I mean, still don't understand, because what do I have to lose, right? Let's do something. If it's I know there's gonna be a lot of bugs here, but dot rec x comma y minus equals self dot capacity. Like, what do I have to lose? I mean, it's not working anyways, so x comma y is not defined. Yeah. That would be x comma y equals pos dot get underscore x pos dot get underscore y. Okay. And we can do, yeah. class, we shall do math.floor x comma math.floor y. Okay. So it's still not cleaning up anything. So it should decrease it by self dot capacity, right? What if we do equals, I don't know, 0 every time? So this should basically clear everything. Okay, so this does clear everything up. So maybe in my init, where is robot? Of course, I'm so dumb. Holy shit. So this is a single type, right? Okay, so we set the position. Now we do self dot room dot clean underscore time. Oh my god, I forgot the method name again. What was the method? Clean tiled position. Okay, now it should work. Holy, that took me a long time for a bug that was stupidly simple. Clean tile at position pos comma self dot capacity. It better work right now. There we go. I mean, sure, it's 0 tiles clean, but I know it's gonna. There we go. Beautiful. Beautiful. Oh, absolutely beautiful. Yeah, it's a very inefficient robot. I'm gonna be real, bro. Like towards the end, holy, it's inefficient as hell. Hopefully, we'll write subclasses of better robots, like better models, because this is hella inefficient. Yeah, look at the time that it's gonna. Oh my god. Oh my god. Okay, okay. One more. Last one. There we go. Nice. Okay. Now let's test this one out. This is furnished room. Should be faster because I have less tiles to clean. Brilliant. It's almost 50% done. Come on. I got it. Do. Oh boy. There we go. I want to see it clean. There. Oh, yes. Okay, cool. So it works. It actually works. I'm just gonna run the test cases. Where are the test cases? There it is. There we go, only 6 errors and 11 failures. So let's see. PS5, P5, 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 P5. Yeah, the rest of it looks fine to me. It's just P5 that's the problem. The rest of it is mostly okay, right? Okay. Now the final problem 4, not the final one. Problem 5 is the final. Implementing a faulty robot. So it turns out iRobot churned out a bad batch of robots. Due to a problem with their vacuums, these robots randomly forget to clean a tile and will change direction. You have been asked to design a simulation to determine how badly this affects the time to take it takes a robot to clean room. Note, faultiness is determined before each time step. If a robot is faulty at one time step, it may not be faulty at the next time step. Add a new plus faulty robot that inherits from robot. Just as standard robot inherits but implements a new movement strategy, faulty robot should have its own implementation of update position and clean. Check if the robot is faulty at this time step. If the robot is faulty, it does not clean the tile it is currently on and have randomly update its direction. If the robot is not faulty, treat it like a standard robot. Head move to a new position and clean it. If it cannot validly move to the next position, instead change its direction. We've written a method gets faulty and set faulty for you that you should use in order to determine if the robot is faulty. Initially, the robot is faulty with a probability of 0.15. As with standard robot, you may find the get underscore new position method of position helpful. Yep. Okay. I have a feeling that the code is gonna be super similar, so I'm just gonna copy and paste it. The only thing is the robot gets faulty and so and not self dot gets gets underscore faulty. So let me check. Oh, so we can do this. So it should update regardless, right? The direction. So if self dot gets underscore faulty, else I can probably write a better code, but you know. Should work now. Let's see. There's a better way for me to check. I mean, this is sure. I mean, but if I just do this, self.p, right? Or set underscore faulty probability, right? So I'm just gonna, for the sake of it, self dot set underscore faulty probability. I'm gonna pass in 1. Oops, pass in 1, so there shouldn't be any tiles that gets cleaned, no matter what. Yep, it works. Okay, good. Now we have the final problem, which is problem 5. Okay, creating the simulator. In this problem, you'll create code that simulates the robot cleaning the room up to a specified fraction of the room and output how many time steps are needed on average to clean the room. Once you've written the code, problem 6, you'll comment the results of your simulation. Implement run underscore simulation according to its specification. Use an empty room for this problem. Each robot should start at a random position in the room. Each robot should start with a uniform amount of dirt on each tile given by dirt amount. The simulation terminates when a specified fraction of the room tiles have been fully cleaned, i.e. the amount of dirt on those tiles is 0. Okay, if you want to see a visualization of your simulation, similar to the pops up and you call this, check the end of this piece set for instructions. Okay. Your code should simulate the robot cleaning process for the specified number of trials. Simulate the robot cleaning the room until a specified fraction of the room tiles are clean. Mean coverage the fraction of clean tiles to total tiles in the room. Keep track of the number of time steps it takes in each trial to reach mean coverage. Output the average number of time steps needed to clean the room. The first 6 parameters of surround simulation should be self-explanatory. For the time being, you should pass standard robot for the robot type parameter. Then in run simulation, you should use robot type instead of standard robot. Whenever you wish to instantiate a robot, this will allow to easily allow the simulation to run with different tools which you'll encounter in problem 6. Feel free to write whatever helper functions you wish. Again, you may find the provided get completion and method useful. Don't forget. Okay. Damn. So still a lot left. Oops, I am in VS Code, right? Yep. Okay. Expected to be done with this by now. Clearly I'm not, so there's that. Let's do it though. So for num in num underscore trials, basically, right? For each robot. So for robot in num underscore robots. Okay. Mm, okay. R, so R equals robot underscore type. And what does robot underscore type take? It's the same for faulty robot, for standard robot. So and for normal robot also. So it takes room, speed, and capacity. Room, speed, and capacity. And room itself takes room, speed, and capacity, right? And room itself takes width, height, and dirt amount. Width, height, and dirt amount. So room equals rectangular room width, comma height, comma dirt underscore amount, right? And then robot type takes in capacity, room, comma capacity, comma. Oh my god, let me just do a second check. Room speed capacity, room speed capacity, room speed capacity, room speed capacity, speed capacity. There we go. So we have our room and we have our robot, right? So we have that for each robot. Now we're gonna run the steps. So if room dot get num underscore cleaned titles. Okay, I'm just gonna add that as a variable. Clean equals room dot get underscore num cleaned titles, right? It doesn't return. So we have that. What was the thing? F equals fraction equals clean, divide that by room dot get non-titles, right? if fraction less than if fraction is greater than min coverage, then steps equals 0. So we're gonna do r dot update position and clean. Update underscore position and clean steps plus equals 1. And then finally return we're gonna return the mean, right? Return steps, divide that by num underscore trials. No. Let's see if the code compiles. If it does compile, then we'll yeah, it doesn't even compile, so int object is not iterable. I see. For I in range num trials, happy. For j in range num robots. Okay. Now what, brother? Ay, ay, ay. It says room dot articles. Okay. Okay, buddy. Let's see. So we have standard robot. Standard robot room speed capacity. In room we have rectangular room. Or was it a bad idea to create rectangular room? I do not know. Didn't say anything on the problem set. Empty room for this problem. Empty room. Yup. Empty room. Okay. Let's get it. It runs. The average time is 0, which means that my code is running pretty fast. But now this should be interesting. Failed 17. Yep, so these are all the fail. So yeah, P Hmm. Yeah, it's crazy. It shouldn't be. Hmm. That is interesting. Yeah. Right. Clearly, this not should be. It shouldn't be an if statement. It should be a while. Fraction equals. Yeah. Interesting. So apparently that doesn't take any time. Apparently that doesn't either. Hopefully this takes some time. Nope, this doesn't either. Maybe this will take some time. Nope. Clearly there's something wrong here. Let's try to debug it properly. So our number of robots is 1, our speed is 1.0, our capacity is 1, our width is height, our height is that, and or okay, let's try to. So this is number of robots, it's 1. Speed is 1.0, capacity is 1, width is height, width is 5, height is 5, dirt amount is 3. Our minimum coverage is 1.0. Does that mean? That means that I want every tile to be clean, right? So it definitely should take some time. But clearly it's not. So let's see. Print could be less than, right? Let me just. So we have the clean tiles, which is 0 in this case, and the fraction, which is so it's gonna be, yeah, it should be, yeah, maybe now we'll get some. There we go. Running all this should take me a decent chunk of time. Okay, so for some of them, a lot of steps. But now the main thing is, does it pass the test cases? Fail. Some of them it fails for reasons that are unknown. This one also fails. Some of them passes. Some of them fails. We have 7 failures. I'm gonna make a cup of coffee and then I'll be back. buddy. Let's go. Let's see. So it fails 7 test cases. This is pretty hard thing to debug, I suppose. So it's a standard robot, right? So it's 5 robots. Speed is 1.0. So that is interesting. Let's see. Mm, mm. Okay, so I think my understanding of the problem is faulty because it simulates the robots cleaning the room. So every robot will take turn, right? So let's do this. for I in range num underscore robots, right? And we can do robot equals this. Robots dot append robots dot append so my width, height, and dirt amount is gonna be the same, right, for every time I create a room. So if I create this earlier room, right, robots dot append is the robot type, right? Yeah, robot underscore type, and then in here we can do room speed and capacity. So we have our room speed and capacity. So we get rid of this loop. We have our outer loop. Okay, so we have so what we want is one step for each robot, right? So while do this, and then no, oops, steps plus equals 1. Yeah, and then in here, so we're not gonna have any R, right? Because we're gonna do for R in robots, right? So it does 1, and then it keeps doing that. And then since it's number of robots, so it's gonna be steps plus equals 1. And if my fraction by that time, if it's less than minimum underscore coverage, then I break. When it doesn't really matter, to be honest, because I'm gonna take one. If I entered this loop, I think I take already one step, right? So please don't get stuck in an infinite loop, I beg you. Oh, why is it stuck in an infinite loop? So this is creating one robot. So print robots. Okay, this part works. Actually, for each trial, I'm gonna have to do this, right? So let's do create roles. So create a room, create all the robots. That's what it says, right? Yeah, each robot to start a random position in the room. Okay. So I create all the robots, and then to clean, I get the number of. For each robot, I do the cleaning for each robot. Then the next robot does it, and the next robot does it, and then the next robot does it, and then once that's done, it's a step. But this is getting me an infinite loop for some reason. Either that, or it's definitely getting me an infinite loop. So fraction is never less than minimum coverage according to that. Let's see, where does it cause the problem? So if I do print robots here, that doesn't seem to be a problem. Oh, it is printing 2 out and it should be 1, right? Wonder why. Okay. It's interesting. Print R. Yeah. It's the same robot object. Oh, I see. Wait. This is interesting. So for that R, I'm calling update position and clean, right? So is it changing the shared room that they all have? It should, I guess, because it says room and then speed and then capacity, right? So by my understanding, is a better way to check that out. Let's access the internals. R dot room dot rec, right? Okay, buddy, that was a bad idea. So I need to make sure that it's happening for each robot. So each robot's own internal room is being changed, or the room itself is basically being changed, right? Hmm. Shouldn't really matter much. I guess. SGL3. So it's hmm. Hmm. Okay, so let's first of all, I should at least update. Why is I 0? What the hell? That's crazy. I think I know why I 0. Because there's only one robot, and the one robot is um So, oh, this is taking so much longer. I thought it would. Yeah, we're close. We're close. So, right now we have one robot. Now, let's try to step through this. Do steps equals 0. We have one robot. We append it to a list with robot type and capacity. And then we get the number of clean rooms and diffraction. And as long as the mean coverage is that, so the first robot we update position and clean, right? And then clean basically says for that robot for R. For the first test case, it should work because it's essentially the same code. But it's basically outputting that we're not cleaning anything. Update position and clean doesn't take anything, does it? No, it just takes himself, which is R itself. And then for robots, we do have robot type append or room, speed, capacity. Let's see if I mess that up. The last time was a simple error, so it is room and then speed and then capacity. So we're passing in the correct thing, and for room it's width, height, and dirt amount. So width, height, and dirt amount. And robot type, right? And for R in robots, I don't get what's wrong with it. Because this is pretty interesting, I would say. Let's try to refactor some things out. Clean is equal to room dot num underscore cleaned tiles, and then fraction equals cleaned divided by room underscore dot underscore get num tiles, and then steps plus equals what if we just do this? What if it doesn't really make it diff? Okay, apparently it does. I don't know why, but it does, so I'll take it. This is probably like me just coding and somehow it working out, which is crazy. This is not, this is also one robot. This is also one robot, so 563 and 712. Okay, then this is, how many robot is that? Also one robot. 584 and then 711, and then this this one is taking longer. 1260. This is the main test though. The last one is 3 robots at the same time. Maybe it'll happen faster. Should. 3 robots working at the same time. Should be less steps. Let's see. Yeah, it is less steps. Okay, maybe right now we are good. Right? Okay. Okay. Please work. Please work. Nice. 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 If this doesn't work, this is gonna be a hell hard block to fix. This is 20 by 20 room, which is 400 squares. Nice, it worked. So this robot's slow, so it's gonna take a long time. Nice, okay. 10 by 10, 3 robots of speed 0.5. Nice. 5 start. Okay. Okay. Nice. Okay. Nice. Nice. Okay. Nice. So it passed basically all the test cases. That is pretty cool. Man, hella satisfying. Okay, now use your simulation to answer some questions about the robot's performance. In order to do this problem, you'll be using a Python package called PyLab, aka Matplotlib. If you want to learn more about PyLab, please read this tutorial. For the questions below, uncomment the function calls provided at the very end of the problem set and run the code to generate a plot using PyLab and then answer the corresponding question underneath the function calls in ps3.py. Okay. Examine show plot compare strategies in ps3.py, which takes in the parameters title x underscore label and y underscore label. It outputs a plot comparing the performance of both types of robots in a 20 by 20 empty room with 3 units of dirt on each tile, an 80% minimum coverage with a varying number of robots with speed of 1.0, including uncomment the call to. So depending on your computer, it may take a few seconds for the plot to show up. I'm not doing the optional part. So yeah. How does the performance of the two robot types compare when cleaning 80% of a 20 by 20 room? Okay, so we run this. standard robot should be fast. But how much is the question? Okay, so this is the time slash steps and then the number of robots. What do we have here? So it follows the same pattern for the given number of robots, right? So you can write based on the graph, we can see that it follows a similar pattern regardless of the number of robots we have on the room. The standard robot always outperforms the faulty robot. Taking up less steps. Is there anything else that we can write to this? Let's see. You can write some reasons behind this as well. The reason for this is because standard robot will clean a tile 100% of the time if it is eligible, right? On the other hand, a faulty robot will not do that. Performance gap remains same regardless of the number of robots. Let's see if we can quantify anything. Yeah, so oh, I can see. So for one room, for let's say 2 robots, right? It took around 1047. The faulty robot takes around 150 to 200 more steps every time. Actually 15% more steps every time. Mathematically speaking, that should be the truth, right? Because probability was 0.15. 0.15. Okay, now the second one. How does the performance of the two robot tip compare when two robot cleans 80% of rooms with dimensions 10 by 30, 20, 15, 25 by 12, and 50 by 6? It should be like similar, right? Because let us see though. Whoa. Oh, yeah, there we go. Okay, let's get it. Where am I going wrong? Oh. Okay. From simulations. You can interpret it as an integer. So I need to add some test cases. I don't know. What's the point zero come from? Shouldn't be the point zero, but there is apparently. I mean, not just interesting, I suppose. We can add some error check. Int width, and then we can do int height. Yeah. Okay. See. So this is gonna take a while. Brother. How long is it gonna take to freaking plot? Holy. Should it take this long? My 10 by 30 is smaller than 20 by 20. Shape width and height equals 300 by width. Width comma height. Height my laptop. Height. Holy. There's no way it's taking this long. It is absolutely no way it's taking this freaking long. Like, it has to be stuck in an infinite loop. Wait, this. Honestly, I'm just gonna do this. I'm gonna modify the internal code because there's no way this is not like it doesn't make a difference, but and then yeah, whatever int I have, man. Oh, I don't know if that's gonna make a big difference. So, oh my god. Hmm. It's doing 200 tries. Oh my god. I'm sorry, but I know it's probably doing something interesting, but I'm gonna do something here. Print. Probably gonna make it slower, if anything. But who cares, man? Yeah, STRI. B. Capiche. Okay. STRI. Nice. So you can be able to at least see that it should go till 200. For each width. So yeah, it's gonna take a long ass time. I suppose results are gonna be accurate, you know. Why is it slowing down at one point? So that way we'll be done with the first one, and then the second one, and then the third one. Because it's gonna take us some time. One 67, 169. One 99, 200. There we go. No, it's a different dimension. And it's 300 by 20. What is that? Some dimension. Right? So at this point, I can go and make lunch and then come back. Okay. I had some food um, while it was running. I looked at the output, right? So it seems like it follows basically the same trend. So mentions it follows the same trend. The standard robot significantly better than the what do you call that, faulty robot, right? Mm, no matter what aspect ratio is, the faulty robot performs around 15% worse. Okay, I mean, okay, let's look at the individual shape itself, right? So first we have 300 so width by height. Width is 10, so 10 by 300, so 1:3. So 1 by 3. Hmm. Let's see. From the say 10 times 30 and 20 times 15, there is a linear increase in the number first value. Value I 10 times 30 with the aspect ratio changing. The width decreasing the height accordingly. First value. I think this is a pretty okay answer, maybe. I don't know, it doesn't seem that bad. Okay, with that being said, I feel like I'm gonna we're done with this P set. So P set 3 is finally done. I don't care what the visualizing thing. So we're basically done. I'm just gonna so we're gonna start on lecture 8.
The fo-
Right? So I'm gonna watch this lecture basically. And then maybe start with P set 4 and then try to finish it today. So I'll do that in a bit. um, so yeah, I'll watch this video right now. I'm gonna mute the audio here because I don't even have my face cam up, so it's like all I'm doing is streaming a full video without even like any sort of remote reactions. It's um that's why I want to like at least remove the audio for this video, and then after I'm done with this video we can just solve pset 4, right? That lecture was really interesting. Yeah, the fact that population standard deviation is equal to, or sample standard deviation is a pretty good estimate of um, population standard deviation, and then also the fact that when you increase population size, it doesn't really change anything. Um, that's pretty crazy to think about, right? The way it works mathematically speaking, right? And then the whole idea of how to calculate standard error is also pretty cool. Um, that being said, I feel like I can do pset 4 now. So let me download the files and then let me start on that. Okay. Nope, main display. Display capture. Yep. Okay. Let's start with pset4 and let's try to finish pset4 actually. Okay, let's get it. Okay, in this problem set, you will design and implement a stochastic simulation of bacteria population dynamics and reach conclusions about how various treatment regimens affect the spread of the bacteria based on the simulation result. You should submit code for your solutions ps4.py, write up the for discussions for ps4 underscore write-up.pdf. Okay. Bacteria are single cell organisms that reproduce asexually. Okay, some bacteria cause diseases, some are harmless, and some are beneficial. Bad bacteria can cause infections, the strep throat, and tuberculosis. Bacterial infections are treated with antibiotics targeted to kill only the bad bacterial cells. Bacteria that cause infections can resist and develop a resilience to antibiotics in 2 weeks naturally and via inappropriate use of antibiotics. Thus, populations of bacteria can undergo substantial evolutionary changes with a single patient over the course of treatment. In this problem set, we will make use of simulations to explore the effect of introducing antibiotics to the bacteria population, determine how best to address these treatment challenges within a simplified model. We'll implement a highly simplified stochastic model of bacteria population dynamics within a person. Nevertheless, our model exhibits biologically relevant characteristics and will give you a chance to analyze and interpret interesting simulation data. We provided you with skeleton code in ps4.py. Please do not change any of the provided skeleton code except to delete to do after writing your implementation. Okay, implementing a simple simulation, no antibiotic treatment. We start with a trivial model of the bacteria population. The patient does not take any antibiotics and the bacteria do not acquire resistance to antibiotics. Simply model the both of bacterial population inside a patient if it were left untreated. Implement the simple bacteria and patient class according to the behavior described in the docstrings in the provided code. Okay. Simple bacteria class maintains the state of a single bacteria. You will implement the following methods according to the specifications. Init is scaled and reproduce. Use random for generating random numbers between 0 and 1 to ensure that your results are consistent with ours. And during debugging, use random.seed0 so that your results are reproducible. And put this at the top of your file. All random cells will be the same each time you run your file. Same way each time you run, which can be useful for debugging purposes. Make sure to remove this before you hand in your PC. The patient class maintains the state of a bacterial population associated with your patient. You will implement the following methods according to docstring spec. Init get total population and update. How many problems do we have? 2, 3, 4, 5, and then the write up, which is 6 problems. Okay, it's not the worst, I suppose. Yeah. So okay, simple bacteria has a birth probability and a death probability. So we just do simple dot birth underscore prob equals birth underscore prob and then death underscore prob maybe. Yeah. Right. Stochastically determines whether the bacteria cell is killed in the patient's body at a time step. The bacteria cell dies with some probability equal to the death probability each time step. Okay, so how to design this basically. So 0.6 is basically the, not 0.6, but like probability that has 0 to 1. So if it's 0.1, then every 100 population, one bacteria. That's right. If it's 0.01, right? It's 0.1, every 100 population, 10 bacteria are going to be dead. It's something to do with the probability. So we can generate a random number. If you have a death probability, we can generate some random number. So we're going to generate random number. If random number is less than the, so that's like a pretty good way to stochastically determine it, right? So if it's 1, then it's gonna be greater than R like every time. So look, 1 could reach 1, I'm pretty sure. It might, who knows. Stochastic means whether the vectors reproduce at a time step called by the update method in the patient class. The bacteria cell reproduces the probability self. Okay, if this bacteria cell reproduces, then reproduce creates and returns the instance of the offspring simple vector which is the same birth and probability rate as its parents. Okay, so it does not reproduce. So interesting, I guess. P equals self dot birth underscore probability times 1 minus population density. Then we can have a random variable. If P is greater than R, that means time to give birth to a new one, right? Return simple bacteria self dot birth underscore prob self dot death underscore prob, else raise no child exception. The bacteria didn't give birth. Okay, let's see if oh, for fuck's sake, module name numpy, so we have to install numpy. Let me install that, then I'll be back. So we have to install numpy. Okay, so we fixed the whole Python issue. Now it runs, or it doesn't. Interesting. Did I mess anything up? Okay, yeah, it should run now. But there's only 3 test cases, and I'm guessing I need to do way more for these test cases to pass. So hopefully whatever I wrote is correct, and we can get into writing patient. Right. So representation of a simple bacterial patient does not take any antibiotics, and his/her bacterial populations have no antibiotic resistance. Whereas bacteria, list of simple bacteria, the bacteria in the population. Okay, interesting. Max population, maximum possible okay, so self dot bacteria and all spark you self that, and then max underscore pop. Okay, get the current total size of, yeah, that's simple. Oh, the current get the size of the current total bacteria population, right? Return len of self dot bacteria, right? Okay, so the final code to write for problem 1. Update the state of the bacteria population in this patient for a single time step. Update should execute the following steps. Determine whether each bacterial cell dies according to its kill method and creates according to the kill method and create a new list of surviving bacterial cells. Calculate the current population density by dividing the surviving bacteria population by the maximum population. This population density value is used for the following steps until the next call update. Based on the population density, determine whether each surviving bacterial cell should reproduce and add offspring bacterial cells to a list of bacteria in the patient. New offspring do not reproduce. Reassign the patient's bacterial list to total okay, I mean, it's a lot, but it doesn't seem like it's gonna be that hard. I mean, each bacteria cell so is kill method, right? So we have, so let's for b in self dot bacteria, right? Okay, for each b, if b dot is underscore killed, if that is true, then we can have a new bacteria. If that is not true, right? Okay, not, there we go. New underscore bacteria dot append b. So pop equals to pop underscore density equals to len of new underscore bacteria, divide that by maximum population, which is self dot underscore max pop, right? And then for b in new underscore bacteria, right? So okay, so each server. Let's see. How do you use value errors as a control flow in Python? I know I can probably catch so yeah, try except, right? I forgot this. Okay, so try patient's bacteria to the list of surviving bacteria, right? So b dot reproduce pop, b dot reproduce pop, right? Pop underscore den, and then add that to new underscore bacteria. Actually, we clearly don't want to do that. Remaining so add that to remaining. Dot append b, right? Except I think inside the except. Okay, so except we raised, what error did we raise? No child exception. Except no child exception. Continue. So keep doing that, and then in the end what we can do is some risky business here. So self.bacteria is gonna be empty. Now we are going to do for b in new underscore bacteria, right? Self.bacteria.append b for b in remaining, self.bacteria.append remaining, and then in the end we can do return len self.bacteria. Okay, I don't know how to test this out right now because I am sure this is just gonna be 3 errors, right? Maybe. But I hope my function is correct. I suppose I can ask AI and be like, do you think this is okay? But let's see, let's just look at if it's okay or not by ourselves at first. So we are doing init stochastically finding out. This can be, I mean, depending on the test cases, I might have fucked it up, you know. I mean, I wouldn't know. And I think I'll just ask AI, make it be like, don't write code for me, you know, just guide me as like how a professor or a TA would, so that I actually learn instead of just copying and pasting. I feel like that's the best thing that I can do, because the test case is not test this, and I don't want situation where like I'm towards the end of the P set and then I have to worry about like every possible thing, right? Okay, I mean, it has a very valid point. Um, so let's do this new underscore b. So this is what it said, that I'm not really capturing the return value, which is true. I'm not. So and this is another error. I'm passing the whole list. Supposed to pass just the individual bacteria. Other than that, I feel like my code is pretty good, right? Now let's move on to the second problem. And I feel like for the second problem we can use the test cases. Okay. In this part, you'll understand the behavior of a group of bacteria cells as time passes before introducing any antibiotic to a simulation. Include the function calc, understood population, or simulation without antibiotic according to the behavior described in the docstring provided code. While you must implement calc, you're not required to use it while implementing simulation without antibiotic, though you may find it useful. You can test, okay, using the test suite we have provided. At the end of your simulation, you use the provided helper function to generate a plot of your result. The plot should display the average bacteria population over time. You plot the average population across number of trials so that the resulting curve is smooth and show a general trend rather than particular of any trial. It may take a minute to generate the plot. Ask you to return a 2D list of populations at each time step for each trial with populations ij. So would be the population for trial I at step j. This means that if you're running 2 trials for 5 steps, okay, fair enough. Problem 2. Okay, doesn't look that big. Let's try to get at it. Finds the average bacterial population size across trials at the time step n. list of bacteria population IJ is the number of bacteria in trial I. Interesting. The average bacteria population size at the time step n. So okay, so something like this for I in yes, for I in range len populations, and then for in range n+1. Put plus equals populations I j count plus equals 1, return total by count. I mean, I hope it's correct. Let's see. Failures 1, error 2. That's confidence interval. I don't expect it to pass. The average, I do expect it to pass. It's not supposed to get 762.5. It got 690.83. Okay. So I'm guessing this is population. Okay. I don't know. So each population, I am going through the steps, right? Or each sample size, whatever. I mean, suppose what we can do is I don't know, I'm just trying out things because I this is way out of what we wanted. If I'm saying it for n steps, population for that is that much. For n steps, population for that is that much. For n steps, population. Perhaps till then, who knows? She knows. Ay, 762.5, and this is disgustingly off. It's still the 299th step. This is gonna be a long ass problem set, huh? That was gonna be easy because I saw it was pretty small. So standard deviation, simulation with antibiotic, which shouldn't be that tough, and then analyzing a simulation with antibiotic, and then the write-up, of course. It says calculate the mean, so first step 100, second step 115, third step 112, fourth step 129, fifth step, and we'll go till that step. And again, I keep going through all the steps till I get it, and then I'm like, oh, I got it, right? Going through all the steps till I get it, and I'm like, oh, I got it. And I keep doing that basically, right? That's what we did before, right? What is this? This is saying that there's like a count. That's the number of steps that we took, and total is whatever the total value is there, right? And return total by across trials. Okay, so it's gonna be, let's say, total plus equals population I, right? And we keep doing that. Oh. And we append that to the mean, right? Total, let's do n plus 1. N plus 1. We append that to the mean. And in here, we do total equals 0, right? And then later we can do mean, divide that by the sum of mean, and divide that by the length of mean, right? And then failures 1. How? Oh my god, 693.1466 instead of 762. Where am I going wrong now, brother? Rather by, for the sake of it, len populations. Maybe that'll save it. It's the same thing in the end. Well, what if there isn't enough count at that step, right? So we can definitely do count plus equals 1 and then count, perhaps. You know, what if we ran out of it? Be a possibility, right? Nope. Don't get any 762, brother. I don't know what else to do. And what else is there to do, to be honest? It's just calculating population average. How hard can it be? Apparently it's I'm actually kind of stuck here because this is a very simple function, but I don't know how to debug this because since it's so simple, everything seems like I'm doing okay, and then not even calling any other separate function. So it's not like and we can do and things so that really makes that big of a difference. Still gonna be incorrect. Yep. And no debugger works here. I suppose I can debug it manually. What am I even supposed to print out? Like, I don't know. You get what I'm saying, right? I mean, sure, in the end, they can have some arbitrarily huge population. So I'll print that here, perhaps. Right, and then this is just normal function, right? So call that sure print population comma population actually comma n in my case is 299, right? So 299, I can call that, and if I call that, then what do I get? 690 point something. I suppose I can do this. I mean, what do I have to lose? Yeah, it's a lot of values. Let's see. Okay, then I'm gonna have the entire output, which is fair enough because there's a lot of values here. Now let's do smaller size. If I did 2 here, what will my function return? Let's try to calculate that. So instead of 200 and something, let's do 2. Right. Or we can do 1. I mean, that's fine as well. So 100 plus 100 plus 100. I see a pattern here. Plus 100 plus 100 plus 100 again, 100 again, 100 again, 100 again, 100 again. So it should return 100, right? So if it returns 100, it means that it's working for some n, right? Maybe not 299, but for some n, it's definitely working. Why am I getting 100, 115, 100? Maybe I missed some there. I do not know. Let's see. The first one is 100, that's for sure. But the second one is 115. Absolutely not. It's 100. There's no way it's 115. Maybe I'm onto something here. 115. Not in the terminal. In here, 115. Yeah, it's only 1115 the entire list, but somehow it's printing out 115. So there's something wrong, right? Yeah, 0 0 for 0 0 it's 100, for 0 1 column 1 n plus 1. I want n. How much? Think I figured it out. Okay, so for n this is correct, so it's not n plus 1. I managed to figure that much out. Okay, 299. So when it's 299, it's 690 point something. which is arbitrarily false. Shouldn't be 6. Bro, this has got to be the hardest problem set that I ever did. Holy fuck. Ain't no way I'm having this much trouble. Oh, my head hurts. What? How am I supposed to calculate this? Like, I don't even understand now. It looks okay to me. Like, I genuinely don't see what's wrong with my function right now. The n thing was wrong. It's gonna be n plus 1. I mean, n plus 1 was wrong. It's gonna be n, but like, other than that, like, let's do this. Let's do print len population I. Okay. I just want to see something out. So it's 300 every time. So for basically for 299, we're looping through the entire thing. From 0 all the way till 299. Fair enough. And for all those values, we're adding. So for that particular example, how is this not working? Like, what? Where am I going wrong? If all of them are 300, then what am I doing in the end? I'm adding all of them, right? Let's see. The last one should be 761 for the first case, right? If count equals 300, print population ij, right? Let's see if it captures the last one correctly. What the? The count never reaches 300, which is 299, I suppose. What? How? I'm doing count plus equals 1, so print count. I don't need the population for now. And I don't need population ij for now. Let's print count. It reaches till 298. Okay, which is correct, which is actually correct. I don't want the whole thing. I want till 299 steps, so 298. I suppose we start count from 1. Is that gonna fix everything? No, it doesn't fix anything. Um, len let's see, print len mean, print len populations. This should be the same. Yeah, they're both 10. Okay, there's that. Okay, my count equals 1. So we can do if count equals 298, print populations ij. Maybe. Let's see. So we're basically going till the end of the. Hey yo. 763, not here. 63. What? 772. Right. I know why. Because right now it can go to 299 because we're starting at 1. Yeah, 772. 732 is also the second last, right? And then so it should be 760. There we go, second last. And so to 760, there is should be 759, 765, right? And then 759. There we go. 753. Yep. 775. Yep. 754. Yep. 774, and then 768. So I genuinely don't know what's like how to fix this. I'm gonna have to take a break because I feel like that'll make me consider possibilities that are probably not catching right now. Probably it's simple. I don't know. For now, I just have no idea how to do this. Okay, let's get back at it. Hopefully, having a fresh set of, I don't know, taking like what, 20-minute break helped, or maybe it didn't. Who knows? I'm gonna play some lo-fi music on the background. Oh my god, not ads, please. There we go. There's lo-fi music in the background, right? How bad does it sound for the stream? Okay. Now let's try to. Hopefully that'll make me less frustrated because I don't know what's going on right now. Like, I don't know why this isn't working. Like, it should work. We're missing something. So there's nothing much given about calculation average, which I mean I understand because it's a pretty simple function. It is one of the simplest one out there. Find the average activations of the population size across trials at time step n. So trial A at time step j. So j is basically the time step, right? Oh, I see the. Oh, wait, I might have cooked. Okay, wait. If I think I realized what I did wrong. If j equals n, add that to the total. Actually, I don't even need to do that. Total plus equals population I comma n. Right, and then my mean is gonna be total divided by n. I don't need count. And there we go. That's why you should take a break. Or I mean, just be an idiot like me, because total equals 0. Yeah. No. Well, so let's see. Time step j. So yeah, there we go. Don't need a mean really. Let's do total equals 0, and then we can do total plus equals population population I, what is it, populations actually. Simpler than I thought. Nice. Holy. I mean, that was interesting, right? Like, I just took what? 20-minute break and solved it instantly, right? Yeah, it passes. Excuse me. Okay. Now what else? Okay. I'm gonna do the whole plotting thing, right? Simulation without antibiotics. Run the simulation and plot the graph for problem 2. No antibiotics are used and bacteria do not have any antibiotic resistance. For each of num trials, instantiate a list of simple bacteria. Instantiate a patient using the list of simple bacteria. Simulate changes to the bacteria population for 300 time steps. Recording the bacteria population after each time steps. Note that the first time step should contain the starting number of bacteria in the patient. Then plot the average bacteria population size y-axis and elapsed times. You might find the make one curve plot function useful. Where is the make one curve? Okay, it's probably up somewhere. It's y coordinates, x label, y label, and title. Okay. We're actually working with matplotlib. So number of trials. Let's do that for n in range. I'm gonna stop the lo-fi music right now. Okay, for n in range num underscore trials. Right. For b in range num underscore bacteria. So all the bacteria are gonna get created. To simple bacteria part underscore prob comma death underscore prob. Okay. Instantiate a list of simple bacteria. So for each trial, right? So bacteria dot append right, and then instantiate a patient using the list of simple bacteria. Patient equals to patient bacteria comma max population. What should that be? Oh, it's given here. Okay, so max underscore pop. Okay, it's not that bad. For so my y-axis on x-axis right now, but that's for one crowd. That will happen for number of routes. Returns a list or list of UDR J. It isn't that easy. I want one graph. Right. Ay, ay, ay. Okay, so let me try to think. I can do something like steps. I can calculate the average at 0 to 300. That's not a problem. Let's try calculate the average and each step. You can do that for number of times, so it should be a float. So let me just try to comment it down. So calculate the average, have a 2D array with average over all the trials, and then so the average of all the trials and generate a step range. Now the population group, that's what we have to return, the time step j. So populate the population graph right now. Okay, so one steps. So for I in range num underscore trials, for j in range close it. We want to do this 300 times, so 300 population dot append a list. So it's a list within a list. Okay, not much works. Now we can do, so we have the bacteria, we can do for I in range 300. Now within that 300, do you want me to do? So you want me to do this is, yeah, population ni equals something. What is that something? It's the list of bacteria, so can we get that? Update, yes, we just have to call update. So patient, this is a method for the patient, right? So let's do patient dot update. Yeah, so now where we get the list of bacterias. Now what we can do is So we have the whole population right now. Now let's try to do the y-axis is gonna be the average. X equals this, y equals this. Okay. Now for the x-axis is gonna be for I in range 3, 1 to 301, right? Because we also care about that specific value. X dot append I. Okay, now for this is gonna be the harder part. We're gonna do for I in range. I'm trying to think actually. So we have a population. So for I in range 300, right? We're gonna use this function. Y dot append population comma I, and this to I'm gonna do 1 to 301, and then for this function we're gonna return population, and let's run this code. It says list index is out of range. Why would you be out of range? There's no way you should be out of range. Clearly you are. That should also go from 0 to 299, right? Then this is also gonna go from so it should be 300 small lists. The way population should look, it should be 300 inner lists within a list, right? Let's see if it does look like that. Good. I mean, it looks okay. We can do something like this: len population, and then we can do print num underscore trials. Should be the same. Apparently they're not the same. So 15,000 for len population. That is so interesting thing. But 50 number of trials, which is very realistic, very, very, very understandable. So it should be 50 lists, right? So something like population 0 dot append 0. So there should be 300 things in here. and in the outside we will do population.append. So actually let's not erase this yet. Yeah, so this perhaps should work. Oh, list index out of range. Why? Yes, because it's not starting out yet. I mean, I was gonna do I, but that doesn't really change anything. Yeah. um, so I dot append 0. If we do this, perhaps it'll work. Okay, one of them is 51 and one of them is 50. And that's fine. One of them is 51 and one of them is 50. Should be equal, so 1 travels -1. And we will also do print len population 0. Should be 300. Okay, cool. You can stop. We can delete this. And then oops, clear this out. Okay, y dot append population comma I, but I forgot to call the function. The function is calc underscore pop average. And there we go. Now let's see. Should take a while, I suppose, but it should. Oh my! Oh boy! Oh boy! Perhaps this is the meta. Perhaps I miscalculated something. How is list index out of range? Total plus equals population. So it's going here. It's going to wider the band, so we're getting close. From my first step all the way till 300th step. If I dare say, if we do this print population, it's going to be a huge as data structure, but should print out. Okay, for some reason, should have been trials -1. Okay, no. Perhaps you can go for it. Come on. Population. Okay. In that case, it doesn't work out. Okay, I mean, what can I do? I'm not understanding these problems that properly. I guess I need more work on lists. Okay. It populated everything, that's for sure. Yeah, I mean, it populated more or less everything, so I'm doing something wrong here, right? Steps. So let's see. And we have a lot of trials. 300, so it's still 299. Sure thing, right? We're in this case. Yeah, I mean, you're passing 301. Actually, it should be just 300. Technically. Work now, maybe. Patient population is there's an error in there. I'm gonna have to fix that later. Oh, for fuck's sake. Oh. Somehow 300 is not working. Why? Why would 300 not work? Stupid boy. Oh. $300 is just not working. Okay, let's calm ourselves down. Let's see what's happening. So since we already have one in the beginning, right? We don't really need num trials. We can do num trials -1. Now when this happens, and we know that's because of n. So it's 300, right? So it cannot reach it can reach till 299. Right, should be the last value. I'm sorry. For n, right? Put it 49 times. This actually goes to 48, right? Because first we have an empty array. Okay, so then we append 0 to it at the 0th index. We do that. We keep doing that till the 48th index. We have to keep doing it till like the 49th index. This is fine. This will go till 49. Oh my god, there's some complicated math going on here that I'm just not understanding, I suppose. I mean, it has been 8.5 hours, but that's not an excuse. Let's see. Um, so, oh my god, I cannot right now, unfortunately. Not now. Later, perhaps. Ay, ay. Mm, let's see. In Python. A nested list, basically. Oh, so you're using what? List comprehension, right? Let's do that. So 0 for range num underscore trials, right? No, not num underscore for 300, and then keep doing that for num underscore trials, and this hopefully fixes a lot of things. It's wrong though. Oh yeah, range is a function, so 300. There we go. Okay. I mean, sure. Print it out. Where's my graph? Oh, because I didn't ask for it yet. What was the function? Make one curve plot, right? So let's call that make underscore one curve plot x comma y, comma my x is gonna be steps, so my y is gonna be what's my y gonna be? That's the average population, and title is gonna be without antibiotic apparently. Okay, antibiotic. Okay, work now, and I don't mind having this. It tells me what's being executed when. Nice. Holy, took me a while, but it's pretty similar. If we do this, perhaps we can have a graph exactly like that. So starts from 0. Or not. I save it. I mean, it is at 0, it's at 100. So I just need to change the label, but I feel like this is fine. So, okay, so we can get rid of the print and move on to problem 3. Holy, took me a while. Okay, using data collected in the simulation from problem 2 as our sample, we want to construct a 95% confidence interval of estimate of average bacteria at a certain time step 0 index. Implement the function calc by confidence interval according to the behavior described in the doc strings. You can test your code. Okay. Mean, standard deviation, standard error, and then 95% confidence interval using sample data collected from running the call to simulation without antibiotic provide. Okay. Running an analyzing simulation with antibiotic. Okay. Hopefully this is easier. So at first, standard deviation. The average population at time step t. Okay, compute average square distance of data points from the average and take its square root. You may not use third-party functions that calculate standard deviations such as numpy or std. Other built-in okay, maybe used. Okay, and then that's easy. We can do that. Variance. I don't need that. I don't need to do that, right? Can just do average equals to calc prop average, right? Calc pop average, calc pop average populations, comma I is my step, and then the average is the data point. So I think I have when we already given a populations, right? We can do something like this for I for j in range populations 0, and then get it inside this our average, right, for that time step that is across the whole thing. So variance dot append population ij minus avg, we whole squared that. Yep, that's for each ji actually. And that's for each that's the whole variance, right? And then we do return some variance, divide that by and then we whole squared that. I mean, we use a root over on that. Right, half or 0.5. Let's see. Whoops. Why are you? Yo, what is happening? Oh, I see. It's because I think I still have it uncommented. Yep. Comment that out. Increase the size. Okay. Yeah, I get that. I meant length of my population. Sorry about that. Okay. Oh yeah, no, I mean tests. Out of range. It's always out of range. Oh. And it even has the oh. It's always out of range for some reason or not. Um Let's start to the area populations. Ij is the number of bacteria present in trial I at time step j. At time step j. So I mean, I think I know what I did wrong. No. You ought to work now. Okay, I mean, okay, so we got incorrect, but at least it's better. So we got 15.57 instead of 10.73. So clearly there's something wrong with our calculation. So I'm gonna do the thing that I did last time. Copy the population and then debug accordingly. Paste it right up here. And then, see what we're doing wrong. So the variance is gonna be I can clearly see what's wrong. I'm not adding anything up in my variance. So variance is, well, technically I'm doing some variance. So I'm doing, and then I'm doing one more average whole squared that. So it is x minus mu whole square, right? For variance, right? Or standard deviation. So that is the variance, right? I mean, if a trial is big enough, we learned that the first standard deviation for one of them is gonna be similar to the other one. That's, I mean, we have nothing to lose. It's not working anyway. So what if we just do this, right? And instead of j, we just do the first one, 0 whole square. And then we just do this. So it's not the worst answer. What did I do? I did 0 and I. right? I let me get my t and length of should be same. I just wanna see. So if I do cal underscore pop standard deviation, what was the it's passing 299. Okay, 299. Okay, so both of them are 299. Oh. So I do my variance, right? Dude, this is very interesting, I would say. variance, and then so we're doing variance of the 10 population, whatever there is that. I think what I'm gonna do is directly calculate the standard deviation. So what is it? It's just root over actually, because I feel like that way it's less likely for me to catch any floating point errors. Plus equals so first it's the normal x, so populations j I minus okay, so minus that with the calc pop average, add in our populations and our ith step. Why is my computer getting slow? I do not know. Oh my god, it's so slow right now. I hate this. I'll work with this, I suppose. And then we are going to do whole square of this. Whole square of this, right? And then we are doing dividing that by t, right? And then not really good. At first you have to calculate the sum. That's what the only n is. Calculate all the sum, like the variance itself, right? To calculate the variance, so okay. towards the end, its variance equals to, I can do std equals this, std dot append. I feel like we're doing the same thing but more steps. Variance divided by t, and then not to mention we do a square root of that. So a square root 0.5 of that. Yeah, I mean, since we calculate the average, one is going to do AVG. And then every time we declare a new variance, and variance, we don't need that. And in the end, we do some standard deviation divided by length of standard deviation, and no root over because we did that before. Yes, so let's see what's the answer or what value we get. Computer's like dying right now, that's why I hate Windows, or like my laptop in particular. I think yeah, there's no print statement here. Okay, print hopefully it'll work. 15 point, oh my god, 15.47 something, and what are we supposed to get? 10.73. So basically we did the whole same thing. We're supposed to get 10 point something. It's acceptable to 10.6 or 10.8, but we got 15, which is like a lot higher. Again, I hate the fact that I'm having such a hard time doing these problems. These problems should be easy. It's just plug and play into the formula, right? But clearly I'm being dumb. Calculating the average propagation at time step t. Oh. Oh. 10 standard deviations. I'm just gonna do this. Okay, it's smoother now. Print test. Yeah, Loki wanna see something. Interesting. So all of them are around 12, 19, 14, 13, 15, 17, 16, 15, 14. Oh, I think I know what the problem is. I want the mean. Okay, so what am I doing? It should be T. Yeah, that's the average, right? Let's see right now what's happening. So I have an average 299 for this sample size. It's this. I add all of these to my variance, right? And that makes more sense to me now. So I'm doing the average. The average is never gonna change. It's for T, right? So I'm just gonna do this print avg just to see that if it ever changes or not. It shouldn't ever change. I know I'm recalculating it. That's waste of effort. Yeah, it's always 762.5. We're not gonna recalculate it later. We're just gonna calculate it once. So that's the average, right? So for each data set, what am I gonna do? I'm gonna do the variance calculation. So 1 is average, whole squared, right? I sum all of these, and only then do I divide it by t, right? However, as I do it, I also do a square root. Perhaps how to do square root in Python. Okay, so this works. So I calculate that, and then I calculate the square root, which is 0.5, right? Half, yeah. And then I print out my standard deviation, which apparently is 177, which is insane to me. Maybe what I'm doing wrong is, yeah, so the same thing that I did with the previous one, perhaps. Instead of bringing over this, and honestly, put this here, right? Remove this, and this is just me not understanding the questions themselves. Variance, right, equals to our population at that point is minus the average whole square, right? And then in the end, this should work, or it doesn't. No, yeah, of course. No, we don't want. We wanna add all these, and then once we calculate variance for everything, we now come on. Okay, I mean, I thought I was smart. Apparently, I'm not. Actually, len of population. There we go. Oh, that took some time, but this should pass. Yeah, so only one error, that's the confidence interval. So let's try to do that. Okay. Finds a 95% confidence interval around the average bacteria population at time t by computing the mean and standard deviation of the sample. Using the standard deviation of the sample to estimate the standard error of the mean. Using the SEM to construct confidence intervals around the sample mean. Populations is the step. The sample mean with 96 times the sample mean. I can't talk to you bro right now. Okay. Let's see now what's up. So we have populations. So the formula is this is standard deviation divided by root over of the number of samples equals calc underscore populations comma d avg equals calc underscore pop average populations comma d, right? So we have that. Now we can calculate. This should be the easiest one, perhaps. Failures 1. 6.65. This is weird. No, yeah. I meant SEM. Of course. Okay. I got some value. That's just bullshit, right? Okay. Test underscore count, not test. 95 CI population, comma ID is 299. Okay, let's see. Oops, semi-standard deviation. Thought I was gonna be done with this sooner. But we still have problem 4 and then 5 and then 6. I mean, we'll get there. my god, I'm so dumb. My this is number of samples, not the average. Perhaps now. Yeah, 1.216 something. Oh. Hmm. So it doesn't seem like it. Standard deviation divided by number of samples, which isn't D, it's ln of population. My brain just stopped working. Oh my god, my brain just stopped working. This should have been easy. If we run this, cool. This was the easiest one. Okay, on to problem 4. In this problem, we consider the effects of both administering an antibiotic to the patient and the ability of bacterial cell to inherit or mutate genetic traits that provide antibiotic resistance. As the bacteria population reproduces, mutations will occur in the bacteria offspring. Some bacterial cells gain favorable mutations like antibiotic resistance. Note that bacteria in lower population densities mutate at a faster rate. Okay. Resistant bacteria. Resistant bacteria is a subclass of simple bacteria which has the potential to gain antibiotic resistance to a mutation. Scientists on the 6002 staff have found that bacteria that develop antibiotic resistance also seem to gain other mutations that cause a different death rate. Resistant bacteria gains antibiotic resistance, it will die with the given death probability. Will die with death probability divided by 4. Okay. The bacteria have this mutation is determined at birth. The methods are innate, get resistant, is killed, reproduce. Okay, treated patient. Treated patient class is a subclass of patient and represents a patient with antibiotic treatment and manages a collection of resistant bacteria instances. Treated patient must make use of the new methods in resistant bacteria and maintain whether the antibiotic is administered to the patient. Treated patient class is the bacteria on the antibiotic. If the patient is on antibiotic, then only bacterial cells that have resistance will. Okay, let's see. The treated patient make use of the new methods in resistant bacteria and maintain whether the antibiotic is administered to the patient. The antibiotic is given to the patient using the treated patient's class set on antibiotic method. If the patient is on antibiotic, then only bacterial cells that have resistance will survive. Bacterial cells with resistance to the antibiotic continue to reproduce normally. Okay, I mean, just a bit more complex than the first classes that we made, and then we're gonna do problem 5 after that, I suppose. Okay, so going antibiotic resistance. Okay, so at first we can do simple bacteria dot underscore underscore init, and then we can do self comma birth probability comma death probability, and then what else? That's it. And then we can do self dot resistant equal resistant, then self dot mute underscore prob underscore prob. Okay. The bacteria has antibiotic resistance. R equals random dot random. Okay. Return. My roommate is calling me for lunch, or for dinner technically, so I'm gonna go have dinner, and then I'll finish this problem set today for sure. There's not much meaning. Then we have is skilled. I mean, I'll come back and do it. 4 should be that hard. Okay. 6:30 p.m. right now. I think I'm gonna give it a shot for 1.5 more hours, and hopefully I can solve the problem set by then. And if not, I'll just do it tomorrow. But hopefully we can. Is killed. Okay. So stochastically determines whether the bacteria cell is killed in the in the patient's body at a given step. Checks whether the bacteria has antibiotic resistance. If resistant, the bacteria dies with regular death probability. If not resistant, the bacteria dies with regular death probability divided by 4. Okay. I mean, so. But I suppose. I can do resistant equals self dot get resistant. Give me a boolean. If resistant, then self dot let's look at our original bacteria class. Right, this patient is killed. If it's killed, and then we can do self dot is killed. Else, I mean, we can return this. Return self dot is killed. Return okay. Reproduce. Okay, stochastically determines whether the bacterial cell produces at a time step. Solved by the update method in the treated patient class. So any bacterial cell will reproduce with probability self dot birth minus probability times 1 by minus population density. Reproduce creates and returns an instance of the offspring resistant bacteria which will have the same will also be resistant. If the bacteria does not have antibiotic resistant, its offspring has a probability of bacteria in. Okay. I'm gonna copy the code for this one because I feel like it's going to be pretty similar. So problem 4 reproduce. Yeah, okay. Now let's see. First I have p equals this one, right? R equals random dot random. P greater than R, then we're gonna okay, so we can do if self dot get resistant, right? Self dot get resistant. If it's true, then we can return resistant bacteria self dot birth prob, comma self dot death prob. Self true. Okay, this should be okay. Hopefully, my class is fine. Maybe I'll have to do the treated patient. I want to check if my class is fine. So okay, so oh, let's just return so that the yeah. So return self dot resistant. pretty simple actually. We can just do this. R equals to random turn self dot depth drop greater than R turn. Actually, let's just do this once. This should be correct, right? Except right, because this will modify it every time I enter, every time I call is skilled function, right? So it's gonna be 4 and then 8 and then 16 and then like 32, so on and so forth. So and just do this, right? And then for safety measures, I'm just gonna do this. What the? Treat as the regular probability, not resisting the probability divided by 4. That's interesting. Let's see. Interesting. So according to the docstring, this should be correct, right? The treated patient class. Let's do this. Okay. Yep. Patient dot underscore init. What do we get? We get self. We get bacteria, and we get max population. Not been given an antibiotic. Okay. Self dot on underscore antibiotic equals false. Self dot set antibiotic equals true. Get underscore disease population with antibiotic resistance. So we have the bacteria here. So we have get resistance, so we can do this. It's a list. Bacteria is a list, right? So for count equals 0 for b in self dot bacteria, if b dot get underscore resistant count plus equals 1, return count. There we go. Let's update this. Patient for single task. So execute these actions in order. Determine whether each bacteria cell dies according to the scale method and create a new list of surviving. Okay, so this is gonna be very similar to our previous one, so I'm just gonna do a quick copy. Whether each bacterial cell dies according to the scale method. In antibiotics, the bacterial cells from so this is true then for B in bacteria. Resistant dot bend if b dot get underscore resistant, then resistant dot bend b. Yep. If blend resistant equals 0, then we'll do this. Else we'll do this pop underscore then equals len resistant, divide that by self dot max underscore pop. Okay. basically the same thing after that, right? Oh yeah, you have to do this. If I mean we can just do this. This time instead of new bacteria we're doing resistant. Okay. If else in remaining self dot bacteria dot append b. Okay, looks about done. So now let's give it a check. If it's done, then we're done with problem 4. So 5 and 6, and 6 is a write up, so 5 is the only code left. Interesting. Self dot on antibiotic on antibiotic. Okay, so let's look at the logic for the update one. We have new bacteria, we have remaining, we have resistant, and so at first what are we doing? We're doing looking at the bacteria. If there's a slight typo here. I meant this to be resistant, and this is remaining. Okay, I feel like it's okay. The code is very complicated and probably not the best lines of code that I've written, but I feel like it should work for sure. Let's go to problem 5. So in this problem, we'll use the implementation you filled in for problem 4 to run a simulation. The simulation explores the effects of resistant bacteria and antibiotic treatments. Implement the function simulation with antibiotic according to the behavior described in the doc strings in the provided code. Use the provided helper function make to curve plot to generate a plot of your result at the end of your simulation with antibiotic function. The plot should have the following two curves: the average total bacteria population size over time, the average population of antibiotic resistant bacteria population over time. Run the two calls in simulation A to simulation with antibiotic that we provide in PS program. First simulation the higher birth probability than second. Now should do. First will converge. The actual approximately plus drastic mirror. So okay. I have a feeling this is also very similar to the old simulation, so I'm just gonna copy paste that code and then modify some things inside of it maybe. And resistant bacteria, and what does that take? It's not gonna show me. Come on, bro. Oh, freak's sake. It takes birth probability, resistance, mutation probability. Okay. Birth probability, comma, oh nice. Death probability, comma, resistant. Is it here? Yep. Comma, mutation probability, and I'm guessing that's also here. Okay. Instantiate a patient. So I'm guessing this patient is also going to be a fancy class of patient. So let's treated patient. Treated patient. And what does that take? Bacteria, comma, max underscore pop. So exactly the same thing. Okay, now can do res underscore population. Okay, underscore is stop. Okay. Okay, and then in here we can also do, yep, and then let's see, I want two curves instead of one, so both the total bacteria population and the antibiotic to curve plot. So it's going to be the same x coordinate of time steps. So for y coordinate, it's going to be one of them is so okay, and then now y underscore 2 equals this. So we can do for I in range 300 to append calc pop average, right? So if population, we're gonna do res population and for I steps, and then now we're gonna do make two curve plot. The first one is gonna be total, right? Total. Next one is gonna be resistant, and this is gonna be average population, this is gonna be X label, and then the value x label, putting time step, and then so time step average population. Then the title will be with an antibiotic. With an antibiotic. And then this is going to return the population and the residence population. And this is probably also going to take forever. I'm going to do print and I don't care about population. Interesting. Clearly something is wrong. I shall take a few medicines and then I'll be back. I don't know. I think I'm kind of sick, so don't know. I feel like I feel like I was getting sick. But yeah, let's try to tackle this right. Let's try to finish till I don't know how much we can. I'm gonna stay here till like 9. Let's say 48. Okay. So we have population and then we have rest population, right? We have X, Y, and then each bacteria we're doing, and then patient equals to, okay, so we're doing patient dot update, and then we're doing patient dot get resist population, right? Well, I feel like this is the perfect time to print population and see where it's at. It's a lot of 0 and 0. Like a huge, actually all of them are 0 and 0. That is crazy. So it is returning. Let's do a print for self-taught bacteria. Oh boy, this is. Mhm. That is not what I want. What's wrong with this? Is there anything wrong with this logic though? Hmm. Well, I can start with one bug. Hopefully, this honestly, I don't know, man. I think I cooked. Loki, I might have cooked here. Okay. Not what I expected. But we have a typo in the problem set. What if we do this? This is definitely because there's a typo. This doesn't make any sense. It should be divided by 4 here and then just greater than r here. I don't know. I feel like that's definitely a typo. Okay, what if we do this now? We run this right now. It doesn't really change anything. My resistant population is just dead. For some reason. Okay, so let's see. 50 and then additional 250. So 150 plus 250. How much is that? Brain ain't working. It's 300, right? It's probably 300, but I'm gonna just make sure. It's 400. Ay, ay, ay. 400. And then this would mean 400. 400. Okay, buddy. See if you work right now. Don't see. Okay. 400. 400. And of course 400. It doesn't really change anything. What if we got it? I mean, it probably won't really do anything if I'm gonna be real. I'm gonna just quit this, man. Yeah, I mean, it's not really doing anything. It's supposed to look like this. Resistant is like literally flat for some reason. Mm-hmm. Oh, ay, ay, ay. Actually, for this, let's see. For this, we actually gonna do 250, right? And then in this case, let's do something. Count equals 0. Right? Hmm. Okay, so that wasn't it. I mean, yeah, it does merge. So, I guess, sure. But it doesn't look correct to me, in my opinion. Let me just do. There's no way all of them are 0, right? That's just bullshit. missing the update probably. Something is wrong with it. Remember that each one according to this skill modeling, create a new list of the surviving bacteria. So that is done. The patient is on antibiotics. Bacteria cell from one. If they're resistant, the patient is not an anti. So resistant or dependent. Right. Calculate the current population density. The value is used. So if resistant equals to population density is this, so for B in resistant. Oh no. This is gonna be new bacteria, new underscore bacteria, and then this is gonna be resistant. Resistant. Okay. Perhaps that was it. Perhaps. Let's see the graph now. Okay, it's actually taking some time to run, which I expect. I expect it to take some time to run. It's not really what I expected. It doesn't actually fall off, and then this is still somewhat at zero for some stupid reason.